Okay, for these people joining this live stream, we're doing a working session, primarily Jonathan, Gorad, and myself, on a problem that we had tried to tackle a few weeks ago about the physics project. We didn't get as far as we'd hoped, and so we're going to try again. And the problem is this. We think that, in general terms, the sufficiently early universe probably behaved as a very high-dimensional, probably the space in it could be thought of as a hypergraph that effectively has a very high dimension, and that as the universe evolved, the effective dimension of space decreased. So our goal is, I think, and Jonathan, you should correct me if you don't agree, what we're looking for is the homogeneous isotropic, do we have a homogeneous isotropic dimension-changing universe? Do you agree that that's sort of the goal?
If we appropriately define what all of those terms mean in this context, then that could be a sensible goal.
Okay, well, why don't we try and make some,
because ordinarily homogeneity and isotropy are defined with respect to symmetry conditions on the metric tensor, but the metric tensor already assumes a manifold structure and therefore constant dimension. So it's
fair enough. Well, what I was meaning by that, at least homogeneous, what I was meaning by that is you make geodesic balls at any point in the hypergraph, they will have the same characteristics. For example, the number of nodes reached at a given radius, graph radius from that node would be the same.
Okay, but that's nothing like the standard definition of homogeneity in general relativity, which is why I think it's important to clarify this.
Okay, well, fine.
Under that definition, the Schwarzschild solution would be a homogeneous solution, which it conventionally is not viewed as being.
Okay, right. Let's understand that. So
any vacuum solution would qualify as homogeneous under that definition.
So but let's say ordinary homogeneity. What is the condition on the metric tensor?
Well, it's
equals constant.
It's invariant under the Euclidean group.
Right. So it's that G mu nu, all components of in ordinary homogeneity, all components of the metric. I'm going to try using our fancy new. Oh, let's see if this works. Does this work? G. Of course, now I have to remember how to type it in this. I don't know how to type it. Never mind. I'm going to type it in the way I normally would type it, because I don't know what to do there. Okay. All components of G mu nu are, or G mu nu, more accurately, G mu nu, oops, that's not what I want. G mu nu of X, basically, are independent of X. Is that right?
Right. But yes. But specifically, you're talking about the scalar invariance. You're not talking about the tensor invariance, right? The isotropy is talking about tensor invariance. Homogeneity is talking about scalar invariance.
Right, but it's saying all individual components of G mu nu,
right,
are independent of X. So then isotropy is that if I take G mu nu and I apply a rotation to it, then it's invariant under that, correct?
Right.
At every point, G mu nu is invariant under rotations.
Exactly.
Okay.
And so for the particular case of Einstein manifolds, then those become conditions on the scalar invariance and the tensor invariance of the Riemann tensor.
Okay. So in particular, that R mu nu presumably is okay. So for the
no, but that's the point I'm making, is that R mu nu is not if you just base it on R mu nu, then as I say, any vacuum solution would be homogeneous. Would be homogeneous.
I understand, because R mu nu equals 0 in the vacuum. But so then there's some more complicated condition on the Riemann tensor for these things. Is that right?
Right. So what you're talking about is a condition on the Ricci scalar, which is a necessary but not sufficient condition. You also have to have the same condition on the Kretschmann scalar.
Which is what?
Which is the part. So when you do the trace and trace free decomposition of the Riemann tensor into Ricci and Weil parts, the quadratic scalar invariant you get from the Ricci part is just the ordinary scalar invariant you get from the Ricci part is the Ricci scalar.
Okay.
And the quadratic scalar invariant you get from the Weil part is the Kretschmann scalar, or at least it is related to the Kretschmann scalar.
Okay. All right. Okay. So what the point being made is, in ordinary general relativity, the Ricci part, the Riemann tensor has Ricci and Weil curvature parts. And you're making the point that in any vacuum solution, the Ricci part is 0, so it trivially has these properties. The question is, does the Weil tensor have those properties? Is that correct?
Exactly. Yeah. So ordinarily we wouldn't, something like the Kerr solution, we would not say is homogeneous and isotropic, even though
definitely.
Right. Even though R mu nu is constant. All projections and all scalars of R mu nu are constant.
Well, R mu nu equals 0 in the vacuum.
Right, which is and 0 is a pretty good constant.
Right. Okay, so the vacuum has R mu nu equals 0, so is trivially homogeneous and isotropic, in quotes. Even e.g. for a black hole. But C mu nu, that's the usual Weil tensor, isn't it?
Yes, except it has 4 indices rather than 2 for Ricci.
Okay. But the Weil tensor is non-zero. And the question then is, so is it correct that the condition for homogeneity is that the Weil tensor is independent of position?
Yes, effectively, yeah. Well, okay. Because the condition is that the whole Riemann tensor should be invariant under the action of the splitting group. And so if the Ricci part is trivially invariant to the Weil tensor.
All right, okay. So to achieve full homogeneity isotropy, Riemann tensor is invariant under the Euclidean group, which means, i.e., translations and rotations. Okay, I understand. Okay, so now, so in the ordinary, Friedmann, etc. universe, we are assuming this. So in that universe, there is a single quantity, usually called A, that characterizes the Riemann tensor. Is that correct?
Strictly speaking, you're basically right. I mean, strictly speaking, there is another one, which is the K parameter, the discretized curvature parameter.
Oh, yeah, right. Okay, so in ordinary...
But yeah, effectively, you're reducing 10 independent components of the Einstein tensor to 2. That's what you're doing.
Okay, remind me, okay, so there's a scale parameter, and the whole Riemann tensor is characterized by the scale parameter A and the dimensionless, what is it, curvature? I mean, it's basically, is it positively, negatively, or neutrally curved, so to speak?
Right. It's not.
What's that parameter called?
It's normally called the discrete curvature parameter to emphasize exactly the fact that you only care about its sign.
Okay, question. Why does that? How should I understand that? That's some kind of symmetry. It's some kind of symmetry type thing that's reducing it to those equivalence classes.
Mhm.
Is that right?
Right, exactly.
Is it obvious why that happens? That there are just those three equivalence classes?
Yes, because when you enforce this condition that you want all components of G mu nu to be invariant under translations or rotations, if you consider it in the kind of in the flats, or if you consider it for the ordinary Minkowski metric, it matters. The only freedom you have is essentially the signs of the dt's versus the dx's.
Okay. Yeah, okay. Other than that, okay, fine. All right. Okay. Okay. I think we understand how this works. All right. Now let's go take the jump to not hyperspace, but to whatever, hypergraphs.
Right.
And what we're looking at here, so what is the analog of this FRW setup for the limit of one of our hypergraphs? So
right.
what?
Sorry.
Go ahead.
No, I was just going to say, so gratifyingly, we have a construction of the Riemann tensor for the hypergraph case, which means we can pretty much translate the definition directly. So for us, well, okay, the approach that I adopted, and I don't that maybe I'm not claiming it's it's the best approach, and maybe possibly Jean or someone else will come up with a better one, I'm hoping. But the approach that I found worked best was to construct the sectional curvature tensor, which is in ordinary Riemannian geometry, the sectional curvature is equal to the Riemann curvature up to some factor that's given by some inner products. So they're components of one completely determine the components of the other, so you can basically treat them as interchangeable. And so then if you're thinking about if you think about projections of the Ricci tensor as essentially being like average distances between points on geodesic balls, that's another way that you can think about volumes of geodesic tubes, right? Is you could if I'm at point X and I want to project the Ricci tensor to point Y, I can construct two geodesic balls at points X and Y, and then I can figure out what's the average distance between between corresponding points on those two balls, and that will tell me whether. And if I look at the discrepancy between that average distance and the distance between the centers of the balls, that will tell me whether the geodesics are being pushed out, pushed in, right, or are changing. So that gives me a general way of constructing the Ricci tensor. So then the sectional.
Wait. Let me just get the overall picture of what we're talking about here. So what are we trying to achieve here? We're trying to discuss how to compute the Riemann tensor, or what?
Yes. Well, I mean, we ultimately want to obtain Riemannian geometry, right? That's kind of what we.
Right, but just to say, in ordinary FRW, there is actually another parameter implicitly, which is the dimension. Right?
Right.
Okay, so here's a question. Just naive question before we get on to the construction of the Riemann tensor. If I just set up FRW in different dimensional space, how do the equations change? We looked at this before, didn't we?
Right. Yeah. So I have a section of my first relativity paper about that. There's a fairly explicit formula for how the two differential equations, the two Friedmann equations, modify.
But they have the same. Should we pull that up and just look at that? Let's see how. Hold on. I can pull up. Ugh. I thought this was in this area where I've been collecting d-dimensional formulas. But did you do you want to point me to the right thing?
I'm pretty sure if we go back, I'm pretty sure you snipped out a screenshot of those equations and put them in one of our previous working notebooks, but I don't remember which one. But if you have those collected somewhere.
I do.
It may not have been in the last. I think it may have been the discussion before the last one.
Okay.
But we'll.
Why is it so big? We generated some giant graph here. Oh. Yeah, okay, this was a not very promising thing where you thought we were, oh, come on, where is it? Well, okay, let's find it again. All right, shall I look back at your paper?
Yeah, you can do it. It's on page 50.
Okay. Okay, page 50.
So it's there.
That's it.
Yeah, 144 and 145, those are the two Friedmann equations for the scale parameter. And yeah, if you make, for instance, the assumption that the curvature parameter is 0, and that you have some non-zero cosmological constant with with this ordinary cosmological equation of state, then you can derive an FLRW equation by just integrating those two.
Okay, hold on. That was too fast for me. Okay, so n is the dimension here. Let's start with the basics. N is the dimension. There's still only one k parameter. It doesn't sprout more kinds of discrete dimension parameters in higher dimensions. Is that correct?
Discrete curvature parameters.
The discrete curvature parameters. Yes.
The distinction between hyperbolic, elliptic, parabolic is independent of dimension.
Okay. Okay. All right. So that would even be true in one dimension.
Would it? In as much as,
well, actually, you see, in 1 and 2 dimensions, these things vanish. Look at that.
Right.
So I think the equation protects itself. That is, it becomes degenerate in Jean is saying nice progress on sectional curvature if you read his emails.
I have read his emails.
Well, maybe he should join us here and tell us what he has to say. Okay. Anyway, so I'm kind of interested by the fact that these things blow themselves up in one dimension. This equation has nothing to say, right? It's just saying 0 equals. I wonder what it actually does in one dimension. Okay. All right. Well, so let's see. Check out our chat, Jonathan. And then I want to okay, so hold on. So these equations, I mean, can we say rho equals, okay, remind me, in Friedmann-Robertson water, P is equal to 0, right? It's dust. Is that right? No, it's radiation. No, it's P equals 1/3 rho.
Right.
It's radiation. Okay.
Yeah,
so
the cosmological equation of state parameter as I described in equation 146.
Oh, that was the equation I wasn't yet looking at. Okay. Yes. Okay. So, okay.
Okay. I still don't completely understand the point you were making about one dimension, but maybe that's whatever.
Well, look at the equation. I'm just saying this equation These terms.
Obviously it degenerates in one dimension because all one-dimensional manifolds are isometric to lines, so they have no intrinsic curvature. And so the Riemann tensor has one component, and that component has to be 0 because the Riemann tensor is skew symmetric. That's a standard property of. There's nothing to do with it.
Fine. I'm just trying to understand what these equations. I'm trying to understand these equations. That's a useful thing for me to get to anchor it. Is everything degenerates in the specific case of one dimension, even though 0.9 dimensions would still do something interesting. See what I'm saying? It's not it's the specific case of one dimension for some reason, not dimensions less than 1, for example.
But the notion of okay, fine. Yeah, okay, if you say so.
But sorry, go ahead. What were you going to say?
Well, if you have a dimension less than, if you have a 0.9 dimension or something, then that means that you have effectively whatever it is, a quasi-Riemannian metric that's isometric now to some punctured open subset of the reals, which is also still isometric to a line. So the same argument still applies as far as I'm aware. But
so you're saying that for n less than 1, you would expect this wouldn't work. Is that what you're saying? I mean, I'm trying to understand. I'm just trying to understand. Is this a specific thing about n equals 1, or is it something about n less than 1?
Well, okay. So several things, as usual, several things need to be clarified here. First of all, in this equation, n is a topological dimension, not a Hausdorff dimension. It's important that we don't confuse those two, because you're talking about Hausdorff dimension. So that's not the n that's appearing in these equations. So if you had a Hausdorff dimension less than 1, the topological dimension would, well, in that case would be 0, presumably, in which case the Riemann tensor isn't defined.
I see. Okay, fair enough.
Because I mean, in effect, you have a tensor, but it has no possible projection directions. There are no indices. So it's unclear what that means.
We were going to ask Jean to join us here. So if you have somebody send him the information, please.
Yeah, we're working.
Okay. All right. Okay. Great. Okay. All right. So what happens? I mean, just very naively, in these equations, if we just believe these equations, I see there's probably an n dot term which we're not seeing here. Am I making sense? That I mean, the final thing we would expect is something that looks a bit like these equations, but has a time-dependent n. Is that correct?
Well, for the Hausdorff dimension, sure.
But do you think that, I mean, for our ordinary universe, the Hausdorff dimension and the topological dimension are the same, are they not?
Well, isn't the whole point of this conversation to ascertain the cases in which they're not?
I understand, but the derivation, would you not expect that the derivation of this would go through, if you were to do this from a d-dimensional, well, let's figure it out. Okay, all right, fine. I mean, there are two different questions. One is the static d-dimensional hypergraph, and the other is the, I mean, I admit I'm a little confused here because we've got two different things. Okay, go ahead. Do you think you have a Jonathan, can you give these guys Jean's email address, please?
Yeah, okay, sure. But what? Sorry, what? I'm very confused about what's happening. What are we asking?
Let's solve that problem first, and then we'll solve the problem of okay. Or I can find it if nobody else can. Do I need to find it?
What? Sorry, I thought you just told me.
Okay. Good. Okay.
No, sorry. Did I misunderstand?
Done. No, you understood. It's all under control. Okay. Great.
Okay. Okay. Fine.
Okay. Now let's go
There's a
back to
problem?
this. Okay. So now, okay. The problem before us is our exercise is for a hypergraph evolving according to our kinds of rules with this.
I think just like last time, I think we do agree on what the question is. I don't think we
Okay.
need.
All right. Fine. So then why don't you go ahead and run the effort to answer the question?
Well, I thought that's what we were doing before you went on to
Okay.
this equation.
Okay. Go ahead. All right. So.
Right. So
yes.
Okay. What?
Go for it.
Yes. Okay. So we have this construction of the sectional curvature that I've outlined at length, which, as I say, takes this. We agree on the projection story, right? The Ricci tensor story that I just described.
I think so. But
yes.
What's the big architecture is? You're saying find a okay. This is derivation of the Riemann tensor, basically. Is that correct? You're describing a way to go from the hypergraph to get a Riemann tensor. Is that correct?
Right. Well, to obtain a quantity which, in the appropriate limit to a metric measure space that is isomorphic to a Riemannian manifold, becomes the Riemann tensor. But yes.
Fine. Yes. Okay. So this is the, okay. So do we have code that, given a hypergraph, will give us its Riemann tensor?
Yes.
Okay. Where is it?
If I weren't busy with 100 other things, I would be submitting it to the function repository. But it's the sectional, it's the discrete sectional curvature function that's in the WFR queue.
Okay. Can you just send it right now, just so we have something, so I can sort of vaguely understand what we're talking about?
I can, but I mean, it's not documented.
No, it's okay. It's okay. But we have you here to document it.
Right. You can also just look at any of my papers which use it and see how it works. But
okay. Well, we could do that too, but it'd be nice to actually run it for something.
Okay, I'll see if I can find that. But yes, as I say, it's just. Well, I mean, do you want to know what it is? Or, I mean,
yes, I do wonder. I mean, it's. But rather than describing it in detail, I mean, the end result is going to be you put in a hypergraph and a position in the hypergraph, and it tells you its estimate for the Riemann tensor at that position. Is that correct?
Well, again, so long as you define those terms very, very carefully, yes.
Okay. But in what form? Okay, so if you're sending the code, we can just look at it. But I mean, in what form is it going to?
I do think it's helpful if we actually explain what it is rather than just.
Okay, go for it. Go for it. Explain it. Or
okay.
Is there some place I should look to?
Well, yeah, as I say, any of my relativity papers, any of my recent relativity papers, but perhaps the algorithmic causal sets one is the place where it's described in greatest detail.
Okay, right. Let's go there. Let's go there. I'm going to pull it up. Algorithmic causal sets. Here we go. Coming right up.
Okay. I mean, page 73 is where the pictures are.
Good. Okay. It's the good news is the thing that I always like about having written things in papers is even though nobody else may have understood them, at least I can find them if they're in something that I've written. So let's take that as the victory here, that you can find where it is.
Right. But anyway, so returning to my previous question, do we agree on what the discrete Ricci tensor computation is?
I'd like to go over it again, but let's assume for now
that actually has been WFR'd because the code is much less complicated.
Okay, so this is the code for discrete Riemann tensor. Is that what you're saying?
The code for the discrete Ricci tensor has been.
Oh, discrete Ricci tensor. I thought I've understood I've understood a way to derive that for millions of years based on these.
Oh, okay, no, that's what I was checking. So, okay, if we do agree on that, then it's easy to explain what's going on.
Well, I mean, so my version of that from millions of years ago is its growth rates of sort of geodesic tubes.
Yes, well, I mean that's just the standard definition of the Ricci tensor.
Fine.
Right.
Okay, but so you're talking about something different, or is that?
No, so okay. The whole point of the original formalism that I developed was that there's a way to do that doesn't require an a priori dimension, right? That was kind of the.
Okay, fine. Fine. So should we look at your WFR function for the Riemann tensor?
For the Riemann tensor or the Ricci tensor?
Ricci tensor. I'm sorry, Ricci tensor.
Well, you can do. I mean,
Okay. You tell me what to do. Tell me what I should be doing here.
Well, okay. Do we agree on that construction or not? If we do, then it's fine. I can explain the sectional curvature stuff.
I think we agree on that construction.
Okay,
Yes.
So all I'm doing is I'm taking
a bug in the function repository, which is that the this n dash appears as a literal thing. If somebody could note that down, that'd be great. Okay, go for it. All right. Next, please continue.
Right. So you just say you take the same construction, but you remove the dimension. You remove the directionality information from the two balls. Those are defined in the projection.
Okay.
So in fact, you just have a pair of tangent vectors, and then you compute average distances between the endpoints of the tangent vectors. That gives you a 4-component tensor, and that is the sectional curve. And then in exactly the same way, the discrepancy between the distances of the endpoints to the distances between the centers gives you the projection of the sectional curvature tensor. And I was able to prove that does indeed limit to the Riemannian case of the sectional curvature tensor.
So let's just go over this one more time, just to make sure I actually know what you're talking about. Okay, so you're saying take two geodesics, right? That presumably meet somewhere, right? Take two geodesics. Do they meet? Which intersect at some point. Is that right?
Right, and are perpendicular.
Okay, what's your definition of perpendicular?
Perpendicular with respect to the inner product. The inner product is 0.
Okay, but we've got a hypergraph that just has, okay, just make sure we agree on what the definition is. So you're okay, the only thing we can do is to measure geodesic distances between points on those geodesics.
Right.
And what do you mean by orthogonal then?
You take the inner product and you test if it's equal to 0.
Okay, define the inner product.
You take the you define the all pairs shortest paths problem from the endpoint of one geodesic to any point on the other geodesic, and then you measure the minimum of the projection of one onto the other. Okay,
so we're making
a general metric measure space.
Okay, so hold on.
Can you guys hear me?
Hi.
Yeah.
Hi.
Yes, this is actually part of one of the emails I sent Jonathan. Was one of these questions is for that definition of the dot product. I had a similar problem where if you try to calculate the angles from that, if your geodesics are long enough, your angles around the point are very much not 360 degrees. So how is that handled?
What do you mean? That's the case in Riemannian geometry too. You have curvature.
No, if you have dot products between tangent vectors at a point, since they are in a tangent space, that tangent space is flat, so their dot products will lead to 360 degrees around the point.
No, I understand that, but your notion of a tangent space is predicated on an intermediate scale between the discretization scale and the curvature scale. And obviously, if your geodesics are longer than that intermediary scale and are now into the curvature scale, that condition is no longer guaranteed.
Ah, okay, I see. Because yes, the other way is to use that angle deficiency directly for the curvature. Then you can work backwards towards the dot product, which is kind of the direction I've been going.
Because you see my point. You have 3 characteristic scales. So there's the discretization scale, which is the characteristic scale of an individual hyperedge. You've got the curvature scale, which is the scale at which curvature becomes non-zero, and you have the intermediate scale with respect to which you want to define tangent space related quantities. And if you go if you go too close to either boundary, you're going to get weird results.
Right. Let's actually write this down. Okay. So we've got this. I agree that that's a useful distance scales. There's discretization. There's where the tangent space is flat, scale over which, go ahead.
Well, yeah, that's just the linear, what in standard differential geometry would be the linearization scale. Or, in GR would be the scale over which SR holds or whatever.
I see. Okay.
I would also argue that the scale on which your curvature changes can be quite relevant.
No, that one is not. That one is below that level. This tangent space here. You're fitting. It's like fitting a straight line to a curve, right? And then this is the next scale is curvature scale, which is the scale in which you're fitting, a piece of a circle to a curve. If I'm not mistaken.
Right. No, that's exactly right.
Right. So This is the scale at which you can fit any kind of Euclideanized, any kind of manifold thing to it. This is a straight line, this is a curve. Okay, this makes sense to me. Now, next question.
And obviously, the place where things get interesting is when the curvature scale and the discretization scale become comparable, then you've squeezed out essentially the tangent space scale, and so it becomes impossible to define ordinary continuum, geometry parameters.
Indeed. And that's presumably one way you will see through to the discrete structure of space-time.
Right, exactly.
Okay, so let's okay, so now can we come back to your, okay, so you're saying we look on the tangent space, the linearization scale, basically, and we've got these two geodesics, and we are making webbing of all the possible, of all of the...
And I should mention, this linearization scale is already implicit in all of the previous constraints, even without caring about, orthogonality and things. It's already implicit in, say, the Ricci tensor construction that you described, because in that case, you need the length, essentially, you want the length of the tube to be at the curvature scale, but you want the radius of the tube to be at the linear scale.
Yes, I agree. Right.
How would you define these things for vectors of different lengths then?
Yeah, that's more complicated. I mean, well, so you mean how would it? Well, tangency you can still define for vectors of different length. That's okay. But do you mean how would I define? How would one define the sectional curvature for vectors of different length?
Yes. So say you're on a sphere and you want to use, for example, for the Ricci curvature, or well, not for the sectional curvature or something like that. If you have a tensor with the input, right, and you have to use long geodesics, so say from the pole to the equator, then that's definitely not in the linearization scale. But
right.
How do you define for example, the dot product on those scales then?
Yeah, that's a good question.
It's complicated, isn't it? I mean, isn't that complicated even in ordinary geometry?
Right, because those would be cases where you're trying to define. I mean, okay, in continuum geometry, that would be like trying to define tangent vectors on two different coordinate patches, which is kind of not.
But also, it's like on the Earth, for example, asking what is the angle between two. I mean, that's a whole elaborate thing. The angle between.
Well, isn't that just the angle between the tangent vectors? Because in continuum geometry, you can take the limit as it goes to zero, which you can't do.
Well, if you mean if it's a great circle path or something.
Yes.
I think it. Yes, but it's going to get more complicated if you're a shortest path on the surface of some weird asteroid that isn't a sphere. I think this rapidly gets much more complicated when you have non-small distances that you're dealing with.
So
okay,
yes, the approach I'm working on, for example, works on scales where curvature is relevant, but the change in curvature is near zero. So that could be, for example, in a sphere, but not on a very strange asteroid.
Right. But I mean that by definition, you're saying the curvature is non-zero, but the change is effectively zero. You're assuming that the space can be approximated by a space of constant curvature, i.e., a generalized sphere.
Yes, exactly, or a hyperbolic space.
Okay, so let's come back to So Jonathan, you were defining what was you were defining orthogonality, and then where were you going with that definition?
Well, no, I'd already gone there. I was just giving the construction of the sectional curvature, and you asked how do I define orthogonality, so I gave the definition of orthogonality.
Okay, can we try it one more time? Your definition of orthogonality. So we take. So we've got two. Vectors are geodesics in this case. So we consider two geodesics that intersect at a point. Okay, then we consider the webbing, as I'm calling it, of every. Let me think. How does this work? Is it the full webbing or is it just from the endpoints?
I don't know what webbing means. I'm saying you take the minute you solve the all pairs shortest paths problem, where one element of the pair is the endpoint of one geodesic, and the other element of the pair is any vertex of the other geodesic, and you take the minimum over those pairs.
Okay, so we're take the end of one geodesic.
I mean, hang on, I can.
It's dropping the perpendicular effectively.
Right. Okay. Take the end of one geodesic, find how far it is to every point on the other geodesic. What is the minimum, which is analogous to dropping perpendicular?
Right. I mean, yeah. If it's really helpful, I can send you all the code for this, but I'm not convinced that actually helps anything.
Well, okay, but then okay, and then this will get you, if that's, it's not how far is it to the point on the other geodesic, it's how far is that point on the other geodesic away from the intersection point. Isn't that correct?
Like I said, it's the projection. Anyway,
yeah, right.
I don't know if it clarifies anything. I've sent you all the code, but
okay.
It's a very simple
email or the
yeah.
Okay, let me see. Does it have pictures of all these perpendiculars being dropped and things? Or not?
No. Like I said, it's my currently 200 large backlog of things to document.
I think you should try and delegate some of that.
I've tried. It doesn't work.
Sigh. Something I say from time to time too. There's an investment. By the time you've got 200 of them, it's worth investing in the delegation process, because if you only had 5 of them, it would be better to do it yourself.
Right. So yeah, there are a few options, but the basic thing is you give it a graph, an initial vertex, and then 2 endpoint vertices, and it will compute inner products. And then yeah, there's a certain amount of freedom of whether you average out over all possible geodesics, or whether you take maxima, minima, whether you normalize the inner product or not, etc. Those are all
okay.
included.
Okay. So these are I don't know what to do with this. We could just put this in here just so we keep it. And can I run this, or is it I mean, if I run it, can I just run it on some random graph, or is it going to?
Yeah, sure.
Okay. Shall I run it on something like a torus graph, or what? Or is that going to be uninteresting? Or should I run it on some actual non-trivial graph?
It's up to you. I mean,
well, tell me what's going to be interesting. I mean,
I'm not convinced that any of them. I mean, it's an inner product. It's not that interesting.
Okay. All right. Fine. All right. Okay. But okay. So we've got this idea of how to find orthogonal geodesics. Got it. Now what?
Right. Okay. So then my previous sectional curvature definition works. Right. You're effectively parallel transporting a pair of orthogonal geodesics.
Let's walk through it again. Okay. So first find pairs of orthogonal geodesics. Okay. Then you can set up parallel transport as the claim.
Right.
Because you can make.
So in particular, I can look at the average. I can look at the average distance between the endpoints of those geodesics, and compare that to the distance between the origin points of the geodesics. So it's a directed version of the Ricci tensor construction.
Okay.
And that discrepancy is related to this in the continuum geometry. In ordinary Riemannian geometry, that discrepancy is related to the sectional curvature tensor in a very direct way. And so all we're doing is we're doing the analogous construction here for the arbitrary metric measure space case.
Okay, can I just walk through this one more time? So we've got a pair of orthogonal geodesics. And what are you saying? You're saying you're transporting No, go through what you're doing with those things. You've then got balls that you're transporting along those pairs of orthogonal geodesics, or what?
No, it's a directed version. It's a four index tensor, so it's not.
Okay, so what exactly do you do then? You've got a pair of orthogonal geodesics. That's
well, I've described it, and I've given you several pictures. I mean, what
okay, what picture should I look at?
Any of the pictures on the page I pointed out.
Okay, all right.
So
Let's see if I understand them.
So like, okay, take that, take the positive curvature example, right? The one underneath.
This one here.
Yeah, the positive curvature example. So you've got two pairs of geodesics, the purple, orange, and the red, yellow. Then I compute the discrepancy between the average, the distance between the endpoints given by brown and blue, and the distance between the origin points, which is purple. And that discrepancy lets me compute the sectional curvature tensor using the equation shown in 224.
Jonathan, it's more obvious to you than it is to me. Can we go through this one more time? Okay, this thing here, is this one geodesic or is this two geodesics? This orangey thing.
Wait, which orangey thing?
Well, let me make it bigger so we can discuss its color more explicitly. Okay, sure. This thing here, this brownish, whatever you call it, whatever that color is that two geodesics with that intersection point, or is that one geodesic?
That's one geodesic mapping from the endpoint of the purple tangent vector to the endpoint of the red tangent vector.
Wait a minute. This thing here is a tangent vector, is that right? This thing which has this kink in it is a tangent vector. Is that true?
No, that is the geodesic connecting the origin points of two pairs of tangent vectors.
Okay, hold on. Okay, this thing here, which is also purple, is a tangent vector. Is that right?
Well, okay, so look at on the diagram on the left, as it says in the caption. You've got two pairs of tangent vectors, the purple orange and the red yellow.
Okay, all right. See now that what you're doing, this is in like if you do user experience testing, right? It's like you actually watch what people do when they interact with your product. So right. You consider this UX testing for this. Of course, I didn't read the caption, just like people don't read the instructions when they open a box with a computer in it or something. Right. Okay, all right. So anyway, so this here. So
all academic papers should undergo A/B UX testing or something.
Yeah, and they'd all fail. Almost all of them would fail. Okay,
right.
So there are 2 points here. These are the points that you're dealing with. Right.
So in the Ricci tensor construction, those would be the origin points for two geodesic balls. That's the undirected case, right? That's the case you would get if you took the average of all possible pairs of tangent vectors at those 2 points.
Okay, I understand.
So here we're doing the directed case of that undirected construction, which gives you the sectional curvature.
Okay, hold on. You go too fast. I think I can get this. Okay, so in the normal Ricci tensor case, what we've got is a tube that goes from a geodesic that goes from this point here to this point here. And at every point on that tube, we puff out a ball in all directions. You're not doing that. Instead here, you are erecting this essentially, what do you call it? Coordinate axes effectively that are a particular choice of a pair of orthogonal geodesics at that point. Am I correct so far?
Right. And so just like in ordinary Riemannian geometry, if you take the trace over indices of the sectional curvature tensor, you recover the Ricci tensor. If you take the average over all possible pairs of tangent vectors, you get balls, and therefore you recover the Ricci curvature.
Okay, I think I'm understanding it. All right, this is an achievement. Okay, so hold on. Let me try to going through this again. Okay, so the normal thing you would do is here you would just have a ball, right?
And in fact, I mean, I have pictures of that. If you go up a bit on pages 68, 69, I've got pictures of that construction.
You see, this is okay. Oh, beautiful, magnificent. All I have to do is to read it. Okay. So that's the case of balls. Beautiful. That's lovely. Now I've lost my mouse. Help. Where's my mouse? There we go. Okay. So this is case one. This is the case where this is the full Ricci tensor case involving a tube traced out by balls.
Right, exactly.
Okay.
And so the important thing, again, is to note that this construction can be done in a way that is entirely independent of dimension, unlike the NKS construction.
Which construction can?
The Ricci tensor and the sectional. I mean, all these constructions can be done in a way that's independent, that doesn't require you defining an a priori dimension.
Okay, explain.
Right. Well, because in the NKS case, you look at the volumes and you compare against exponents of those, and that gives you a dimension.
Yep.
But this construction takes discrepancies between lengths, which is measuring the same quantity, but without you having to know a priori what the dimension is.
I see. That's nice. Okay, I need to understand that. Just hold on one second. So the point here is that we are taking a small slice of this thing here. This is constructing the Riemann tensor, yes?
Right. Yep.
And by, instead of transporting a whole ball, transport, what are those things called? They have a name, and the coordinate, just a little, what are they called? Frames? No, it's not really that. Is it a frame? It's like a frame in differential geometry.
Right. I mean, yeah, so like a Frechet frame.
Yes, right.
Would be something like that, yeah.
Frenet frame, I think.
Oh, Frenet, yeah, I always get those. Yeah, so Frechet equations, Frenet frames, that's right.
Okay, that's very beautiful. Okay, now explain to me the thing you just said about dimension independence. So you're saying that this will compute a curvature. Let's just take this case here.
Well, yeah. So in the construction, as I think you define it in NKS and in the in the Gray paper and things, what you would look at is the volume of this geodesic tube. So you would look at just the total number of vertices contained within it, and then you compare that against the volume in a in a flat space.
Yep.
Of the same dimension. So you implicitly need to know what the dimension is.
Yes.
Right.
But does that also implicitly assume that vertices have equal volume element then?
Yes, it does. Yeah, that's right.
Is that a justified assumption?
Well, it can be. I mean, it depends what you mean by volume element.
Right. I mean, yeah, you essentially, you have complete freedom to define what your volume elements are. So you could, just as like, if you had a weighted hypergraph, then you could interpret that as being the case where they're not all equivalent. But
okay,
so for if you're using that construction, you're looking at growth rates of volumes, right? And the way you're defining volumes in that case is by counting vertices. So by making that connection to counting vertices to volume is then implying then directly. So isn't that an always case more? I'm
not sure I understand the question.
So it will always be, with that construction, you're always assuming there's basically a linear relationship between volume and vertice count.
No, which is not necessarily. Well, you could have an arbitrary weighted hypergraph.
Yeah, but the point is, whoops, somebody is echoing. Can you, Jean, I think that must be your, if you use a headset, then you can avoid echoes. Yes, there is I mean, the very definition of what you mean by, you can, Jonathan is saying you could take a weighted hypergraph where one unit of geodesic volume is not just one vertex. But otherwise, that is the definition of the volume of the geodesic ball is the number of vertices that live inside that radius. But I want to understand, hold on. Jonathan was making an important claim here about the definition of the Ricci tensor. So, okay, let's start off with the Ricci scalar. Does whatever you're doing here allow you to define curvature in the Ricci scalar without defining dimension or not? Or does this only start working in the Ricci tensor case?
Well, it implicitly allows you to do that because the Ricci scalar is recoverable from the Ricci tensor.
Okay, but there's no direct derivation.
Not that I'm aware of.
Okay, all right. So then this is very interesting. So because in the usual case, in the Ricci scalar case, right, we're just looking at the volumes of these geodesic balls, and the leading term is the dimension, and the subleading term is the curvature, and that's what we've understood. Okay. Now you've got a different thing going on here. So explain what you have going on here.
Right. So implicitly, that Ricci scalar / Ricci tensor / whatever construction is assuming the existence of a model space, right? Some other hypergraph that you're taking to be flat with the same dimension.
Yep.
You're comparing two geodesic. You're comparing the size of one geodesic ball to the size of the other.
Yep.
But there's a way you can do that without having a model space. And so the way and the approach is you say, okay, I'm going to puff out two geodesic balls at points X and Y, and then I'm going to look at the average distance between points on those two balls, between corresponding points on those two balls, where I could.
I don't quite know what corresponding means.
Right. Yeah. Exactly. One has to be a bit careful about how you define corresponding. So the way that I did that here was just I said we want to find a bijective map from the points on the surface of one ball to the points on the surface of the other ball that minimizes average distance. For instance.
Okay. All right. Fine. Let me just write that down so I understand that. Okay. So we're saying you're finding essentially a distance, but a distance between balls by finding a bijection. So everybody has a friend, so to speak. Why are the balls the same size? How do you know everybody has a friend?
So they're not necessarily the same volume. They just need to have the same surface area, right? The outermost shell has to be the same. It has to be the same.
All right. Okay. Find it by. Okay. First, go get balls with the same surface area. Then set up a bijection between the elements on the two surfaces. Then find the bijection for which the average distance is minimized, right? The average distance between corresponding points is minimized.
Right. Now, the minimization isn't that significant. You just need to, all that really matters is that you have a canonical way of picking such a bijection. And that's a way of doing it.
Minimized. Or it could be something other than minimized.
Right.
Okay, fine. We've got a bijection. Now.
Okay. So then you can look at what is the average. So that gives you an average distance between points on the two balls.
Yep.
Now there's also a distance between the centers of the balls, between points X and Y.
Oh, this is nice. This is kind of tidal force. This is the tide, basically.
Right. Exactly. Yes. So in GR in the Ricci case, it would give you a projection of the tidal tensor. Yeah, that's right.
That's nice. That's very nice.
So you look at the discrepancy between the two, and the nice feature of it is that although it's measuring the same quantity, and it's quite easy to see that it's measuring the same quantity as the old Ricci tensor construction, you don't need to know a priori what.
Okay, so wait a minute. We're going to construct. I didn't even know there was a tidal tensor, but it's not surprising there is a tidal tensor. By comparing the average surface distance between balls with the distance between their centers. Now, okay, so the claim is that measures, let's see, is this obvious? That's effectively measuring the tidal deformation produced on these. I don't quite understand. Why is that okay.
Well,
explain.
Essentially, okay. Why intuitively do any of these constructions give you the Ricci tensor? Well, in the volume case, the old case, what you're doing is if the volume is lower than the volume of a geodesic tube in flat space, that's telling you that the geodesics are converging, that the tube is somehow becoming concave. If it's higher, then the tube is getting convex, and if it's the same, then it's the same. But the point is, if the tube becomes concave or convex, that will also change. That will introduce a discrepancy. If it becomes concave, then you can reach a point on the other ball faster than you could do if you just traveled along the middle. Whereas if it becomes convex, you'll reach it more slowly. You have to travel greater distance. And so the deformation in the volume also translates to a deformation in the distance. But the nice thing about distance is that you can define it even without knowing what the dimension is.
Okay, so we're considering the bundle of GD6 between these balls. And if the question is, are they converging or diverging? And it's one question of positive or negative curvature.
Exactly.
And the statement is, if they are converging, then it's effectively a long way. There's a long way round to get to the other side of it. I'm not quite understanding this. I mean, so if they're bowing out here, that means there's a long geodesic to get from a point here to a point here.
Right. I mean, so you can actually see this in these pictures. So if you look at that picture you've snipped there, if you compute this, you'll find that the average distance along the red geodesics is lower than the distance along the purple geodesic, and that corresponds to the statement that this space is hyperbolic, that it's negatively curved.
The purple geodesic is the center-to-center geodesic.
Exactly. Whereas if you look at the pictures just above it in the paper, you have the case where the space is flat, in which case the distances are the same, or where the space is positively curved, in which case the distances are greater along the red geodesics.
Magnificent. Okay. So let me just say this again. So what's being said is, it's the comparison. If you want to get to the other side of the Earth, from one Earth to the other, I don't know whether it's Earth to Earth, whatever. If you want to get, from one side of the Earth to the opposite, to the far side of the moon, so to speak. The question is it longer or shorter than you would expect based on the distance between the center of the Earth and the center of the moon?
Exactly.
Wouldn't it rather be the far side of the Earth and the close side of the moon, since you're trying to minimize the average distance? So you want the bijection would usually have them on corresponding sides.
It depends where you're standing, right? Whether you mean far side or close side.
Oh yes, fair
If
enough.
If you're looking front on to the Earth and the moon, it's the near side of the moon and the far side of the Earth.
Yes, so in this one, on the left side of the green ball will be mapped to the left side of the blue ball, for example.
Right. Yeah, that sounds right.
Okay, so again, I just want to run through this one more time, just to make sure my intuition is right here. Okay, so in the usual case of sort of gravity, there is a, you're saying there's a pull, which here we'll talk of as it isn't quite the same thing, but as a distance of geodesic between the centers. And the question is, a tidal deformation comes about, positive tidal elongation means that it is further to get from far side to far side than you would expect based on going center to center. And that corresponds to further to get there. So it corresponds to the bowing out of geodesics, which corresponds to a positive curvature space. Is that correct? If the geodesics bow out this way, that's a positive curvature space. And so when it is tidally, like the actual tide on the Earth, the actual tides on the oceans get further away than you would expect based on, the Earth is elongated this way.
Right.
And that means the geodesics have to go further to get to the end. On the other hand, the other case, the Earth will be foreshortened that way, so the geodesics would have to go less far, which is what you get by diverging geodesics, I think. I got it all the right way around?
I think so, yeah.
Okay, all right, okay. And so your point is, that's very nice. Okay, so this is a curvature independent of dimension. Okay.
Right. And so in the cases where the dimension is exists and is well defined, it obviously aligns with the previous definition. But the nice thing about it is that you can think it's like it's possible to kind of analytically continue to cases where the dimension of the space is not well defined.
Well, so what you might think is that this definition of curvature, maybe, I mean, the question is, in the early universe, could you have almost a fixed curvature, but variable dimension, where this quantity was remaining fixed? But where, so what would this look like? The dimension change here, how does dimension enter this? The dimension enters it by things like the volumes of those geodesic balls changing.
Right, exactly.
But otherwise, it doesn't really care. Am I correct? I mean,
Yeah,
otherwise, okay, so this definition is as independent of dimension as the definition of a geodesic, basically.
Right. Now, this does have the weird, okay, now you get into the slightly subtle area, which is what is the scale along which, so we were previously talking about scales along which along which curvature changes, but there are also presumably characteristic scales along which dimension changes.
Mm-hmm.
And then it becomes relevant how those scales compare, if you want to, discuss this in detail. But
Right. So okay. I mean, this is effectively a thick geodesic, what you've got here.
Right. No, that's exactly the right way to think about it, I think. And in fact, that's by thinking about it as a thick geodesic is how you recover something like the Ricci scalar, because you essentially take this, you take this construction and you average out, you take the Ricci tensor construction and you just average out over all possible, you fix one ball and then you average out.
Right, you just swing the thing around. You take
right.
this big bundle of cables and you're swinging it in all directions.
Right, so you effectively get a ball, but one that is constructed not from thin geodesics, but from thick geodesics.
Right.
Would this scalar curvature be able to be plugged back into volume formula to get a more accurate Hausdorff dimension then?
No, yeah, wasn't it exactly the same? Because in the end, you're just counting as you swing these balls around. You're going to count. You're going to scan over every geodesic that comes out of this generalized point.
Right. But it is it would be interesting to know. I think I agree. In the fully sort of degenerate case, right, where you're just computing the Ricci scalar, I agree. It doesn't. I don't think it's. I think it's rather trivially going to be the same quantity. But it does lead to this question of, which I guess is in part what that dimension tensor project at the Winter School was trying to investigate, of what happens to your dimension estimators if you, rather than just using the full, geodesic ball construction for the Ricci scalar, but you look at something like a directional, dimension tensor approximation. How do those things compare in reasonable spaces? I think there's, I think there's an interesting empirical study to be done of when you estimate dimension using constructions like this, rather than just the straightforward geodesic ball constructions, in what situations do they differ and in what situations are they the same?
Yeah, I agree. But your point about, okay, so wait a minute. Length scales, okay? One scale, there's the scale of the small balls, okay?
Right. So the reason I make the point about the length scales is that, in a sense, implicit in this construction is the assumption that you want the curvature to be varying over the scale of the purple geodesic, but you want the dimension to be constant because you want the two balls to have effectively same, to have equivalent dimension.
Right.
So
hold on. I'm not sure that. Okay, hold on. The scale of the distance between balls at which you swing around to get the Ricci scalar. So the scale on which you're computing with this construction, right? You take this thing, you swing it all around in all directions, and that will give you. But okay, your point is the dimension of this ball you imagine might be the same as the dimension of this ball in order to achieve your bijection in a nice way.
Right. Exactly. But if the dimension is changing over a scale that is the same as or smaller than the curvature, than the scale at which the curvature is changing, that assumption will not be true in general.
Indeed. I mean, you have to set up a different kind of bijection
Right.
between, you could set up a bijection between the elements on the surface of a circle and a sphere, but it's a little weird. It feels very Banach-Tarski like.
Right. And I don't think, well, I certainly haven't done in-depth analysis of how that works mathematically, and I doubt anyone else has. But it should be done.
Okay. So then the point you're making here. All right. So let's go back to our original question, which was the time dependence of dimension. Now, is there? See, what I had been hoping is that we would get a test space on which we could look at the time dependence of dimension that would have the sort of homogeneity and isotropy sort of somewhat obviously. If that made any sense. I mean, the normal. Okay, maybe you had a plan here. So I think I finally understand your constructions. They're very nice. Now what?
Yeah. So I mean, the reason for going through this was to look at the sectional curvature construction, because that's the one that's relevant for defining homogeneity and isotropy. But
okay, well, is there yet more to look at? What is? I don't even know. Okay, where do I have to? Do I scroll down further or something? And then
no. I mean, you already snipped out the the Riemann tensor sectional curvature tensor pictures, right?
What is the sectional curvature as opposed to? I thought a sectional define. What's sectional curvature as compared to Riemann tensor?
Oh, so they're trivially interconvertible, as I say. One determines the components of the other. The intuitive definition of the sectional curvature tensor is that if you construct, it's looking at the Gauss curvature of the if you look at all of the geodesics that are so if you look at all the unit speed geodesics emanating along a given tangent plane, that have origins along a given tangent plane, and you compute the Gaussian curvature of that surface, that curvature is the projection of the sectional curvature along that surface.
But so roughly what it is, you've got a bundle of GD6. It's going through this space. The space is curving, and so the GD6 are diverging and converging and so on. And you slice the bundle of GD6, and you look at that cross section of the sliced bundle of GD6, and the sectional curvature relates to the shape of that slice. Is that correct?
Exactly. Yeah, it's just the Gauss curvature of that slice.
Okay, I understand. Okay, so now where do we go with that?
Right. So to construct that, all you have to do is take this Ricci tensor construction and make it non-directional, right? Or take the two balls and make them make them directional rather than non-directional. So you just rather than having two balls, you just have two pairs of tangent vectors, and you do the same construction. You compute the average distance between the endpoints as a function of the distance between the centers. Oh,
you mean you're looking at this case here?
Yes. So now this is rather than having two indices, this now has four indices, because you have to define the.
No, I agree. So okay, hold on. Let me just ingest this for a second. So you're saying you can do the exact same thing. You can simply ask the question. Yes, that's exactly like parallel transport, right?
Right, exactly. And so then, and it has, it satisfies all the right consistency conditions, and it means that if you now take the average over all possible pairs of tangent vectors, you get two balls, and therefore you recover the Ricci tensor, which is telling you that if we contract over the right indices of the Riemann tensor, you get the Ricci tensor.
Okay, so from the frames, look at the bundles of GD6. That gives Riemann tensor. If you slice the bundle, if you look at a slice, the shape of the slice of the bundle, shape of a cross-sectional slice of the bundle, of a cross-section of the bundle, that gives you the sectional curvature. Is that right?
Right.
Okay, where again, that thing is a four-legged animal because you've got to determine the directions of all four of those legs.
Right. Yeah, effectively, yes.
See, it's very interesting to me that, every leg is a geodesic, basically. I mean, this is, again, what we were talking about last time of sort of paths meet variables in some sense. We don't really have, our tensor indices are always defined by paths. Maybe this is obvious. You know what I'm saying? I mean, normally you have directions in a space. We don't have directions. We just have geodesics, which are more diverse than the possible set of directions. There are, we could have potentially all kinds of geodesics going to all kinds of points. Is this making sense?
Right, but just like with the subtlety of the distinction between Hausdorff dimension and topological dimension, that introduces the subtlety of what about the cases in which they're degenerate. Right. Normally, degenerate tensor indices are not something that one normally considers. But
I agree. But so let's just go through this for a second, okay? So I mean, in a sense, there is a much, in the normal case, you have a tensor and it has, each index can have a certain set of integer values, which are essentially the coordinate directions, right? In some sense. Whereas here, in a sense, every possible direction from a given point is a proto-tensor index value. What do you call the index values anyway? Do you get what I'm saying? I mean, so in other words, let's say we have an x mu. Okay. The question is, what are the possible values of mu?
Yeah, I know what a tensor is.
I know you know what a tensor is. What's the name for those set of possible values?
Coordinates.
No, it's coordinate directions. It's the coordinate, the ith coordinate.
Yeah, but in abstract index notation, the whole point of abstract index notation is you don't make a distinction between those things.
Between which things?
Between the index of a coordinate, of a coordinate component or a component in a particular basis.
I understand, but normally when you say a coordinate, you're thinking of a coordinate value, not the.
Well, no, but that's the whole point. In abstract index notation, you're emphatically not doing that. That's the point of it.
Well,
it also feels like geodesics wouldn't necessarily be indices. It's more like the vectors you're projecting along, right? Because usually you.
I understand, but to turn that into indices, you have to do some orthogonality thing, which might or might not work.
Right, exactly. But yeah,
right,
just like in in all the tensor functionality that we have in the function repository, right? We make it very clear that you're computing projections. You're not computing tensor components. You're computing the r mu nu dx nu rather than r mu nu.
Right. Takes me ages to type this stuff. What's that? Go ahead.
I had a long conversation with Jan Mangleton about whether it was right to call these things tensors or not, as a consequence.
Well, so this thing.
I mean, strictly speaking, those should be upper indices, the dx mu dx nu.
I know. Yeah. Okay, but I can't be bothered to put them there.
Okay.
Okay. Yeah, let's put them there. Otherwise, I'm going to be confused the next time we look at this. Let's see. How do you do that? No, help. That made two of them. Help. Okay, here we go. Control 6 mu. And now we want to remove that. And control 6 mu. Okay. All right. So that's what we're computing for certain dx mu dx nu. But then the question is, can we find orthogonal? Yeah, I mean, okay. So I'm not sure where we're going with this. Do we need this information? I mean, the point here is to loop back to this dimension computation thing. So do we need this? So I think more or less understand how this works. Famous last words. Okay, should we go back to the beginning here and go back to the we were trying to define homogeneous and isotropic.
Right. And so I was just making the simple point that we have a definition, right? It's the same as the Riemannian definition. There's nothing fancy going on.
Okay, so can we find an example then of a hypergraph that is statistically homogeneous and isotropic?
Sure.
Many are.
Right.
So a random sprinkling, e.g., a random sprinkling of any old of what kinds of spaces, or is every random sprinkling homogeneous and isotropic? Probably not.
Certainly not every. It depends whether the manifold is homogeneous and isotropic.
Right. So a random sprinkling of a homogeneous and isotropic manifold will be homogeneous and isotropic. Correct?
Right. In the limit as the sprinkling density goes.
Yeah. Right. We're just we're brushing all limits under the rug.
Excellent.
Although that may yet bite us. Okay. Right. So
I mean, again, just to emphasize, that is why it is relevant to discuss these scales, because brushing limits under the rug gets problematic when you start comparing, scales over which curvature varies versus scales over which dimension varies. Then for these kinds of calculations, actually, whether those limits do or do not commute really does matter. That's not something.
So I'm going to make the claim that the universe we want to consider is one where the curvature and the dimension are constant across the universe.
Oh yeah, no, sure. For the homogeneous and isotropic case, that's exactly what you need. Yeah.
Okay, fine. So then, if that's true, we've got this universe, we've got this hypergraph. It has more or less the same dimension and the same curvature at every point in the hypergraph. Okay, so now the question is, and it's evolving the same at every point in the hypergraph. What is its effective equation for dimension in that case? And is it derivable? Okay, Friedmann, Robertson, Walker is generic in the sense that, well, what do I mean by that? I mean, in our models, right, all of that computationally irreducible flapping around, the equilibrium is just going to lead to the homogeneous isotropic Friedmann, Robertson, Walker type thing. So my question is, what's the analogous thing for dimension change? Jonathan, do you think you have a way to work that out?
I don't understand the question because, I mean, FLRW is also homogeneous and isotropic in dimension as well as in curvature.
Absolutely. It has a fixed dimension, but its dimension is not time varying.
Neither is that of FLRW, other than the time varying of A. But
exactly, but the time varying of A is the story.
Right, but up to conformal rescaling, it has a constant curvature. Or, I mean, essentially, okay, are you asking what is the analog of conformal rescaling but for dimension?
I think that's what I'm asking, yes.
That is an interesting question.
Let's go back and look at that for a second. Okay, explain the conformal rescaling thing. So that's because you say A dot over A. Okay, so the point is, now I'm a little bit confused. Explain the conformal rescaling with respect to those equations.
I don't know what there is to explain. I mean,
Okay, A is is an expansion is a scale parameter, right?
Right. So curvature scales like 1 over A.
Fine.
Right.
Question.
The conformal structure of the Riemannian manifolds on each space-like hypersurface is invariant. So that's
obvious from these. Why is that obvious? Is that obvious from these equations, or is that obvious independent of these equations?
Well, it's obvious from the structure of the metric, of which these equations are the reduced form. These are the reduced Einstein equations for a homogeneous and isotropic line element.
I understand that. Okay, let's get to some basics again. Let's get to basics again. Okay. The statement that it is conformal, this conformal invariance. So if we construct light cones for this thing, walk me through the conformal invariance argument. You're saying you construct light cones for this.
Well, so these equations, the quantities that appear in these equations are defined not on space-time, but on space.
Indeed.
The n is a spatial dimension, the a is a spatial quantity, etc. Okay, so if you take an FLRW space-time, where you have a sort of expanding or contracting universe, whatever, the point is that because it's sort of uniformly expanding or contracting, the whole thing, the whole dynamics of the whole space-like hypersurface is determined just by this parameter a. It means that the light cone structure, if you like, of the space-time is constant, essentially.
Okay.
The conformal structure doesn't change. So all the point being that all FLRW spacetimes with the same discrete curvature parameter have the same light cone structure.
Indeed.
And therefore are equivalent up to conformal rescaling.
Okay, but from at the level of these ODEs, how do we see that? What is the light cone in this ODE? The light cone is determined by a dot.
Well, the light cones are the characteristic lines of this differential equation system.
Right. I'm going to make a
Can I suggest an approach?
Yes, but hold on 1 second here. Okay, so the important point is that light cone structure is independent of time, and it's determined by the characteristic structure of the characteristics for the solutions of these equations. Is that correct, Jonathan?
Right.
And okay, but and how do we? Is it obvious? I'm too rusty on finding characteristic lines, but how do we walk me through the derivation of the characteristic lines for these equations? And is it obvious? Is it from the fact that this appears in a homogeneous way, a dot over a? Is that what causes this, or what causes this fact? That
it's a consequence of homogeneity and isotropy, sure.
No. I know that, but I'm asking just all you're presented with are these equations, right?
Yep.
Derive the fixed conformal structure just from these equations. That's doable, right? Because you can derive the light codes from these equations.
Right. Yeah. I mean.
Okay, but just so I'm clear, okay? How do I derive? Okay, I want to figure out the. I'm very confused here. Okay, how do I erect light cones? So at a given, this describes a spatial slice, right? The equations describe the evolution of a spatial slice, the time evolution of a spatial slice, correct?
Yes.
Okay. So now, at every point in the spatial slice, we can start a light cone.
Right.
What is it about these equations that says that the causal, aka conformal structure of that doesn't depend on time? What mathematical feature of these equations makes that obvious?
Well, the invariance of the characteristic structure. So
I know, but how do you see that from just the form of this ODE?
you compute the characteristic lines and you show that they're invariant.
Yes, I understand that under time. Okay, how do you compute the characteristic lines?
It's the usual way, right? You take a solution A and you construct the surface graph and you take the normal vectors to that surface graph.
Can we just do it with these equations? So,
if you wanted to, yeah.
so I actually understand what's happening. I mean, I'm trying to understand what feature of the structure of these equations is what's necessary to get the characteristic lines to not change with time.
Yeah.
I mean, do you know the answer to that? Is it? I think it's some homogeneity feature of these equations would be my guess, but maybe I'm wrong.
No, you're correct.
Okay.
The way you would prove that formally is by computing characteristic lines using, Lagrange-Choppett equations or whatever, just the standard analysis stuff.
The difficulty is my advantage is that I've done lots of different things over the course of time. My disadvantage is it's a very long time since I computed, since I had any reason to compute the characteristic lines for an equation. In fact, I'm trying to remember when I last did that.
It's not a fun derivation.
Do we have a function that just does it?
I was actually about to look that up. It would surprise me if someone hadn't developed a Wolfram language function for computing Lagrange-Choppett equations.
If they haven't, maybe somebody should. Okay, but okay. So I want to see how that works for these equations. But then Jean said he had a potential approach. So do you want to describe is it still relevant here?
Yeah, sure. So if we think about the scale parameter, if we think about random points in the manifold, then the average distance between these points will be proportional to A, intuitively speaking. So then the other thing that we have, since our graph, our edges are all length 1, the average distance between vertices in this graph will grow as roughly n to the 1 over d. So if we set A equal, well, or is it square root of A? I can't remember the dimensions at the moment of A.
A is a linear. A is dimensions of inverse curvature. Inverse curvature scale. So it's the A is the characteristic length scale in the universe. It's a length.
Well, curvature is 1 over r squared, right? So the square root of A would be length scale. So if we set that equal to some constant times n to the 1 over d, and we tracking how n changes is trivial. So that gives us some idea of how d changes then as well, right? So then we can get this A parameter. If we basically introduce that third equation, A doesn't come from purely say just the content of the universe in terms of energy content and the lambda term. We get this very direct thing of computing A directly from a change in dimension and a change in the amount of vertices in the graph.
Okay, I think I understand your statement. So you're saying, okay, what's that?
I'm very confused, but
let me try and unscramble. Let me try and unscramble. No, I don't necessarily, but let me try and unscramble it. Okay, what is the relationship between the Hubble radius and A? That's a cosmology question for Jonathan. Or
the Hubble, the Hubble constant is just A dot over A, right? The Hubble radius
is A, basically.
Right.
Right. So, okay. So in essence, Hubble radius, which is essentially a radius of the universe, is like A, right? So now what I think Jean is saying is...
okay, there are several things I don't understand, but one is, why is what you're talking about not just measuring the volume of the universe?
Well, there's two different volumes of the universe. That's the point. There's two different things you might mean by that.
Yes, because there are at least 4, in fact, right? Because you've got...
Okay, we can probably multiply up possible meanings, but I mean,
proper physical co-moving or conformal distances, but this is a conformal volume.
okay, so the one volume of the universe is the number of nodes in a given spatial slice. That will be one measure of it. Another is the assuming that the universe is in some sense spherical. Another version of it is something, is essentially an R to the D type volume, where R is the radius of the universe, A to the D or something. Is that correct? So we've got two different things. We've got the number of nodes, and we've got this parameter A, which is measuring the scale size of the universe. But that doesn't get into convertible with number of nodes until you know the effective dimension of the universe. Right?
Yeah. Well, yeah. So if you track, so this is something I implemented quite recently, just empirically. If you basically just track, if you take larger and larger pieces of the graph, how the average distance changes with the amount of nodes, then you get it that it changes as n to the 1 over d. But A is also going to be proportional to that average distance. So I don't understand why we can't just put them proportional to each other. I think I'm missing something.
Okay, so hold on. So you're giving a third version of this. So A, where A is the overall scale size of the universe. Okay, and then you're saying, let's call it, I don't know, Z. Z is the average distance, average graph distance between 2 points. Is that right?
Yes.
Okay, now what is the estimate of the volume of the universe in terms of the average graph distance between 2 points?
Also, I wasn't thinking about the volume of the universe. I think I know what you're talking about that, but that wasn't my direct question.
All right, okay, fine. So this is something different. So that's okay. So then tell us what your version is.
Well, so you say Z is proportional to n to the 1 over d. And
what's n?
N is the amount of nodes in your hypergraph.
Total,
yes.
Okay. So you're saying Z goes like n to the power 1 over d. Yes, I agree. Where n is the total number of nodes. That's the total number of nodes, n. Okay. Yes. So what?
And then my question is, can we then just say that Z is directly proportional to A?
Well,
this is a question of scales. What?
Well, obviously, yes. This is just a less general version of the Meerheim-Meyer estimator.
Yes. So then we get an equation where we say that A is proportional to n to the 1 over d. So we can get an equation for A dot and A double dot with respect to how n and d changes over time.
Yeah.
And since how n changes over time is a question about your rule and your hypergraph state, that then just A becomes essentially a function of how your dimension changes. So that links that to the existing equations we already have.
Yes.
Yes, so that was my
Wait. None of this is as obvious as either of you are making it sound. At least not to me. Okay, so.
Well, hang on. Why is this not obvious? I mean, so the Meerheim-Meyer estimator works by essentially taking the fact that the average distance between a pair of points with respect, well, in that case, with respect to the Minkowski metric, but in my extension of it, it works for Riemannian metrics too, is a function of both the volume and dimension of the manifold, right?
Sorry, I just got distracted for 1 second. Could you say that again?
The way the Meerheim-Meyer estimator works is precisely the fact that there is a relationship between the probability of an average, the probability of an average, the chosen pair of points lying within a certain distance of each other with respect to either the Minkowski metric or to a more general Riemannian metric, is a function of the volume of the manifold and the dimension of the manifold.
Okay. Okay.
Right, because in that particular case, it's, well, for the particular causal set case, it's being used for ascertaining whether a pair of points are causally related and therefore have a, either a positive or a negative Minkowski distance, depending on your metric convention. But more generally, it's just telling you that average distance is dependent on the dimension and the volume of the manifold.
Okay. Mm-hmm.
So in the Meeheim-Meyer case, you rescale by the volume, which is exactly what we're doing here. So it's the same. But the thing that really confuses me is why? I mean, okay, we're talking about a completely different thing here. I thought we were wondering, I thought the question was, how do we obtain an analog of conformal rescaling for the, for the case of homogeneity and isotropy of dimension rather than homogeneity and isotropy of curvature invariance?
Yes, that was a question. But the overall question is, what is the analog? Yes, that's right. But these equations.
So there's clearly something. Sorry, I'm being very, very slow. There's clearly something. So how does this? What's the relationship to
I'm not sure there is a relationship to this. This is addressing. Okay.
Essentially, is if we replace A with just that in those equations, 144 and 145, don't we get an analogous equation, but that talks about the change in dimension?
Yeah, sure.
Isn't that what we're looking for?
What is?
Okay, hold on. Okay.
I'm confused about what the question. I thought the question was fairly well. Okay, sorry. Clearly I'm out of my depth. Just never mind.
Jonathan. Okay. Define. Okay. Let's go back through these two items. Okay. The first question is, it's not obvious to me that these equations, with their versions of D in them, right? It's not clear that D is the same as this D here, is it?
No, it's not. As I mentioned at the start, right? That's a topological dimension, and this D is a Hausdorff dimension.
Yeah. So I mean that right there, so if we want to look at dimension evolution, what topological dimension should we be talking about here?
Right. Well, for the case of geodesics, it's the floor function of the Hausdorff dimension, if you use those as your indices in the abstract index notation case. But whether that's the most general construction, I don't know.
Yeah, it seems very unclear. I don't think these equations as such, they're not going to survive. The equations, there'll be a generalization of these equations which has something different here that isn't, because this is a topological dimension factor that comes from essentially taking traces of tensors and things like this and counting indices, which might generalize to arbitrary, D or might not. Or is it obvious to you, Jonathan, that it does not generalize?
Well, I thought it did, but as I say, I don't understand anything anymore. So
no, wait. What do you think generalizes?
Well, taking traces.
Okay. So you think, in fact, that even though this starts life as a topological dimension, you think that in the end, is it the same dimension that appears here or not?
No.
Okay, but you think its value is related or not?
Well, yeah, it's related at a coarse scale because it's measuring, as I mentioned, degeneracies of geodesics in the projections.
Okay, but do you think its value is the same?
Sometimes.
Okay, but do you think in the case that we're interested in, namely this kind of uniform universe, do we think its value will be the same in that case?
Well, I don't know.
Okay, fine. All right. Okay. All right.
I'm going to nail down the definition of what it is we're asking.
Okay. Again, as far as I'm concerned, what we're asking is this. We have a hypergraph. It is evolving according to some rule. It starts off being this big giant blob of hypergraph is statistically homogeneous. Okay. And isotropic. And the question is, as that blob of hypergraph is updated according to some local rule, it will change the estimates that we would get in it for curvature and dimension. how do those change? Because we know that if we are fixing the dimension, right, then, your fine works have established that the evolution of the curvature should follow the Einstein equations, right? But we're saying if you don't fix the dimension, what then happens? And the point you've made repeatedly is it's not obvious whether we will find equations that independently, most likely.
I don't even know what we're asking, right? I don't even understand the question.
Okay, which part of that question?
All of it. What notion of dimension are you talking about when you say dimension? Do you mean the Hausdorff dimension that appears in the volume calculation, or do you mean the topological dimension that appears in the number of possible ways of projecting the tensor?
No, I mean the one that appears. Look, ultimately, it's
because both are relevant, and the only place in which and the place where they become conflated is precisely in the case where you take traces, right? Because in that instance, you are taking a trace over over say a geodesic wall radius, which is therefore, so that quantity is determined by the Hausdorff dimension, but the trace is taken by essentially projecting in all possible directions, and the number of possible directions is determined by the topological dimension. And so when you take the trace, suddenly it matters how these two quantities relate, whereas ordinarily it wouldn't.
Okay, but what I'm assuming, and I might be wrong, is that there is a single fairly robust notion of dimension that applies to this large hypergraph.
Okay, so you're already fine. But then we should be very clear that you're already assuming a priori that you don't have a fractal structure.
That's correct. We're assuming that.
Not at all clear to me at the start. That was not one of the assumptions you listed.
Okay, so hold on. Another assumption. Okay, so another assumption would be, quotes, it's not a fractal. So homogeneous and isotropic, as Monsieur Benoit was fond of pointing out. Well, actually, no, he didn't point. No. His model of the sort of fractal universe, does that count as being isotropic? I'm confused. No, it's not. It's not homogeneous. It's not homogeneous. As soon as you have, the universe is a giant Sierpinski, it's no longer homogeneous in dimension 3 or whatever.
Again, right? That's sensitively how you define these things. So it is homogeneous with respect to the definition that we were previously using. It's homogeneous and you can have homogeneous and isotropic fractals. Right? Because the only thing that goes wrong in the fractal case is that you end up having geodesic degeneracies, which means that the number of dimensions in terms of the number of possible linearly independent ways you can project tensors differs from the dimension you get in the leading order exponent of the volume element.
So wait a minute. In Mandelbrot's, I even have his book on my shelf. I'm going to look this up because I remember, and I think he changed this between the first and second edition of his book, possibly because somebody told him that it couldn't possibly work that way. But he had some whole thing about dimensions of the universe, and as an attempt to explain Olber's paradox. Do people believe the Olber's paradox? That Olber's paradox explanation? Do you know what I'm talking about? I mean, the
I haven't read his book, so I can't comment.
Well, I'm looking at a thing here that says implementation of Hoyle's model of hierarchic of stellar clusters based on a cascade, blah, 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 blah. The issue of the Olber's paradox is, if there are enough stars.
Right. No, I understand the Olber's paradox. I haven't read Mandelbrot's book. I understand about, why is the night sky not white, but.
And what do you say is the answer to that?
What do I say is the answer to that?
Yes. What is the currently accepted answer to that question?
Well, like an inflationary modification to lambda CDM solves Olber's paradox. But
How?
Well, because it ends up being not.
I mean, this is the universe isn't infinite solution, basically.
Right.
Right. So, what's that?
Yeah, either in space or in time. So it doesn't.
Right.
Yeah.
So there's not a star in every direction, because I mean, so the explanations. I mean, so Mandelbrot had a different explanation. His explanation was, it's not white in all directions because it's not because it's fractal, and the things are clumped, and so you don't get to do that integral. That was his explanation.
Isn't that Chalier's explanation? I don't know.
Whose explanations? What?
I thought I don't know. I thought that was Chalier's explanation, but maybe I'm wrong.
Well, I'm just looking at the page where it says, actually, he says the Charlier universe. That was the previous section here, so they're clearly closely related.
Okay.
Oh, okay, all right, fine. You are correct. Yes, he says Charlier sidesteps the Olbers paradox in a way that's now discussed. Okay, but is that not? I mean, is that still a viable explanation or not?
Well, if it were true that stars were distributed by, using a fractal distribution function, then it would be a valid explanation.
But stars do have a correlation function that isn't as like r to minus 1.8 or something. They don't have a uniform. They're not uniformly distributed.
Right.
But so you're claiming that there's an assumption that we're effectively making here that amounts to something about. Let me explain to me this assumption you think we're making about no fractality.
Well, you just said I'm not the one making the assumption, right? You said I believe there's a single robust notion of definition
of
dimension, sorry, that we can supply for these hypergraphs when they're sufficiently large.
That's my assertion. Yes, that is the simplest assertion.
Right. So that's all I'm just repeating that. I mean, that's
okay. But are you attacking that claim, or are you not attacking that claim?
No, I'm just saying we should be explicit that we're assuming it's not a fractal. That's an important.
Why is that? Explain why that is assuming it's quotes not a fractal. What's your definition of a fractal that would cause that to be?
The standard definition of a fractal: any topological space in which the Hausdorff dimension is strictly larger than the topological dimension. So if you're claiming that the two are equivalent, then it clearly can't be a fractal, by definition.
Well, okay, I would consider that a very mundane definition of a fractal. But yes, I understand. In the pictures in Mandelbrot's book, the topological dimension and the Hausdorff dimension weren't the same.
Is there another definition of a fractal?
Yes, I mean the operational definition for me is a nested structure of some kind. But what you're describing is a more geometrical topological definition. What have generally been more interested in is the more computational definition.
Okay, I'm not quite sure what nested structure means, but
well, it means you make it from a neighbor-independent substitution system.
But like, if I call nest of grid or something, or whatever it is, nest of box,
yeah.
Is that a fractal? It doesn't seem like a good.
Well, yeah. I mean, look, this is the question of whether what is essential is the combinatorial structure of nesting, right? And it isn't very interesting nesting if it's just one element. If one element begets one element, so to speak, it's not very interesting nesting.
Right.
But if one element begets three elements or something, you can have very non-trivial nesting. But that is the combinatorial definition. What you're describing is a potential, but not obviously equivalent, geometrical and topological definition.
I don't know. That's the only definition I'm aware of, but maybe there's another thing I just don't know about.
The definition, okay, this is the problem. The word was invented by a particular person who chose to change the definition over time. So that doesn't help anybody. But I mean, your definition.
In fractal geometry of nature, I thought it was defined as you have a Hausdorff-Besicovitch dimension and it strictly exceeds the topological dimension.
Sort of. I mean, yes, that's a never mind. I mean, that's a question of history of science and kind of close reading of particular texts.
Completely more right, but sorry, so I may be using a faulty definition.
No, that's fine. That is a perfectly reasonable definition. Whether it is exactly what that text precisely says really is unclear. And what's important and whether the combinatorial definition is important, it doesn't matter. For these purposes, we're saying what you're saying, it's not a fractal in the sense that it's topological dimension, whatever that means, because topological dimension is not an easy thing for us to define. I mean, you know, in the hypergraph case.
Well, it is fairly easy for us to define. In many ways, it's easier to define than Hausdorff dimension.
And how are you defining it? In terms of orthogonal geodesics or what?
Yeah, well, yeah, exactly. Just the usual definition.
Well, so by topological definition, dimension, you mean a count of the orthogonal geodesics. Is that right?
Wait,
okay.
So I'm missing something. But so topological dimension is always an integer. So how do we have a field equation then for that?
Well, I agree. It's not. That's partly the point that I'm.
Well, I think the answer is because the definition of topological dimension is going to blow itself up because of degeneracies in geodesics and things like this.
Right, but I also agree with that statement, but that means that, again, we have to be very, very precise about how we essentially analytically extend the definition of topological dimension to non-integer cases, which I agree you can do by essentially quantifying geodesic degeneracy. You can say, I can basically fit two whole linearly independent, I can fit two orthogonal geodesics plus one that's, you know, a bit orthogonal, right?
Right.
But we have to be very precise about what
that means. But I would love to avoid topological dimension because I think it's much harder to define for our systems than effectively Hausdorff dimension. I mean, if we can avoid ever having to talk about topological dimension, I think we will come out ahead. So, I mean, I would be happy if what we could get is an equation for the evolution of the Hausdorff dimension.
Sure. Okay. No, I agree that would be nice. But given that we are starting from a situation where we're talking about tensor indices and things, we'd have to be able to do that without making use of any tensor calculus.
I know. I'd love to not use tensors. I mean, I'd love to have an argument that is basically based on, I mean, okay, the way I think this is going to come out, I think the thing is going to be a fairly obvious, essentially combinatorial-ish argument, combinatorial/statistical argument that is going to, in the end, lead to an equation that is some kind of, I don't know, diffusion-ish. It probably won't be a diffusion equation. There'll be something different. Equation, well, won't be a diffusion. It won't be a PDE. It'll be an ODE that describes, you know, d dot, basically, as a function of time. That's our goal, is to find an equation that describes the evolution of the Hausdorff dimension. So the picture that we have is we've got J-random hypergraph. It's evolving according to some rule. That rule, I mean, we started looking at this before. That rule is, you know, detangling, retangling, whatever it does to that thing. That's the question. What does a typical hypergraph that has some dimension, that has some, you know, geodesic ball-based dimension? Now the hypergraph is being randomly reconnected, like by diffusion. What happens to that dimension?
Right. No, I think we've stated that goal many, many times.
Okay, so now unscramble. What's that?
I have the same objections that I had right at the beginning.
Okay, so go ahead and state your objections.
What do you mean by dimension, right? What does Hausdorff dimension mean? You need to define what the cutoffs are. You need to define what the characteristic scales are. You need to define how you account for boundary effects.
Okay, all right, fine. Let's do that then. So let's be very concrete. Well, let's say we have a million node object and it's flapping around and reconnecting itself and we have a rule that conserves the number of nodes. So it's always 1,000,000 nodes.
Great.
Right?
Okay.
So now, obviously, there is an overall scale. The volume is 1,000,000, right? That's our, now, then we have we make geodesic balls around every point. And at the beginning, maybe the thing has effective dimension 10 or something. So the geodesic balls grow very rapidly as we change radius.
What does that mean? What does it mean to have effective dimension 10?
Okay, so what I'm saying is define, okay, so.
The Hausdorff dimension for a graph requires you defining several scales, which you have currently, as far as I'm aware, not defined.
Okay, all right, okay. So we've got our overall graph, right? Now we start a geodesic ball at a point in that graph, okay?
Right.
Okay, now that we're looking at, and we count the graph distance, 1, 2, 3, 4, 5, right? And you're saying that, and so one possible definition would be fix the graph distance that we're going out to. Okay, we're going out to graph distance 10. It's always 10. And going out to graph distance 10, we are simply fitting V of R effectively, the number of nodes we reach by the time we get to graph distance 10. Let's assume that's our way of computing what we mean by dimension. Now, you will validly say that with 1,000,000 nodes, we might very well run out of nodes. We might hit the edge of the universe before we hit the edge of our geodesic ball.
Well, that's one fundamental problem. Another fundamental problem is that you're incorporating contributions from lower geodesic ball radii, where you're not at the characteristic continuum scale, you're at the characteristic discrete scale. And as I show, as is described both in the documentation of Wolfram Hausdorff dimension and at length in the causal set paper, that causes issues. You get issues both with boundary effects and with discretization effects. And the art of it is defining a low end cutoff, essentially like a sort of a low energy cutoff and a high energy cutoff in such a way as to avoid both of those issues. But those cutoffs are dependent on various, they're not just dependent on the cardinality of the vertex set, they're dependent on certain other features of the geometry of the graph. It's not well, maybe there's some very, very clever scheme that has been worked out that I'm not aware of.
No, but look, the very simple-minded thing is you compute V of R as a function of R. R is the graph distance, right? For small r, you're at the discretization scale, things are weird. For large R, you're at the universe size scale, things are weird, or even at the non-homogeneity scale, things are weird.
Right. And in all of the computations we've done so far, there's very little intermediate scale in which the notion is even definable in any sensible way. Right. Most of the example, the last live stream we did about this, we were computing examples in cases where basically you either are at the discretization scale or you hit the boundary. And so
yeah, I understand. Right. We ran into that problem. Okay. But the goal here, I think, is if we can set up essentially a mean field theory that looks at the infinite size limit, then at least at the level of that approximation, we can, deal with the fact that we have these scales, because we're basically just assuming we're going to the limit of infinite size.
But we can't, right? Because it depends on, again, it depends on commutation of limits. It depends when we go to infinite size of hypergraph. Does that, when you say size, does that mean radius? Does that mean cardinality of the vertex set? And if so, how does the radius of the geodesic ball cutoff vary with that? These are all questions.
Okay. Let's just take this apart for a second. Okay, so the first question is, you have the whole universe, right? And one question is, if the universe has a certain, you have the whole universe at some number of nodes, right? 10 to the 400, a million, whatever it is, some number of nodes. That's the whole universe, right? And the question is, let's say it's 10 to the 400 nodes. Can you fit in to those 10 to the 400 nodes a reasonable range of scale sizes between the discretization scale and the scale at which it matters that you're hitting the edge of the universe?
Right, but again, this is where we need to be precise about what we mean. So if you literally just mean number of nodes, then this clearly fails, right? Because I can just take a star graph with 10 to the 400 nodes in it, whose graph radius is 1, right? And that's just that's not going to converge to anything continuous.
No, I understand. But
Are we taking the limit with respect to the cardinality of the vertex set? I strongly suspect the answer is no. It seems to me much more plausible that you actually want to take the limit with respect to the cardinal. Oh, sorry, with respect to the graph radius, right, for a connected graph. And then we have to define how does the cutoff radius of the geodesic ball vary as a function of the graph radius in that limit?
Indeed.
And then it becomes a well-defined problem.
Right, indeed. So let's assume I was happy to just take, in a first approximation, a fixed cutoff for the geodesic ball. Go out to, I don't know, 20, graph radius 20, let's say. Okay. Meanwhile, the radius of the whole graph is varying. If the radius of the whole graph becomes comparable to 20, we're toast. The geodesic ball that we're using to measure dimension won't even fit in the universe. It's all over.
Right.
Okay. But let's assume that our 20 is small compared to the graph radius of the universe. So now the question is, the thing I'm trying to understand is, the qualitative picture is you've got this hypergraph. It's all tangled up, starting from a given node. There's a certain number of nodes you get to by going a certain graph radius. As you evolve the hypergraph, the claim would be, which I don't fully understand yet, the claim would be that, if we were to plot V of R, let's just talk about V of R. Let's not even talk about dimension yet. We're just talking about V of R. You plot V of R as a function of hypergraph evolution time. Okay? If V of R, the claim that's being made is V of R gets shallower. V of R starts as something that grows very rapidly, like R to the some large value, and that over time, as you evolve the hypergraph, V of R gets shallower. That is the claim being made here.
Right, but you realize already that that's a very non-trivial. The question you've defined is a very weird one, right? It's not the kind of question. It's certainly not the question I thought we started out with. It's a well-defined question. I agree, but it's
okay. What do you think is going to happen in that question? What do you think is going to happen in that?
I have no idea, because your question is asking, we're computing a discrete quantity. You're taking a continuum geometry, but you're only taking continuum limits with respect to one thing, and the other thing you're keeping it discrete. And that's normally when you talk about taking continuum limits, you expect everything to become continuous. You don't keep some parts discrete and some parts continuous. So that's I'm just pointing. I have no intuition for this, because it's such a strange kind of question that's so different to how we normally think about these things.
Well, let's see. I'm trying to remember whether I looked at this.
Right. You see my point, right? That you're computing a discrete volume element, a discrete approximation to a volume element, but in a space that you're claiming is limiting to a continuum manifold.
Sure. I know.
That's a weird thing.
I know. That limit hasn't been done yet. Right.
So I agree. It's an interesting and well-defined question, but I'm trying to justify why I don't have any intuition for how that might work.
Okay. You know what? I have endless pictures of this now that I think about it. I had forgotten this point. Okay. So we have endless versions of this that I computed. Hold on. Let me pull some up. I think. Okay, so that picture there, right?
Yeah, as a logarithmic difference estimator.
Right, but the point is that I have a bunch of pictures that show, what is this? I think those different curves, aren't those the different time steps? I think they are. They're the different time steps in this evolution. That is, Yes, first 10 steps in the evolution of this rule. So this is this picture, right? This is the weird picture, right? So what this is on the x-axis is r, on the y-axis is basically the logarithmic differences of v of r, okay? Each different curve here corresponds to a different time step. So as you see, as the time steps get larger, v of r stays meaningful for longer and doesn't hit the edge of the universe.
Right.
Right.
But this is not a dimension. I mean, we're not, okay, unless I'm misunderstanding, we're not attributing that to a dimension change. We're attributing that to the fact that the graph is getting bigger.
Exactly. Exactly. So in these cases, what's happening? Go ahead. What were you saying?
Which is not the case I thought we were discussing. I thought the whole thing that you were repeating several times was we want to discuss the case in which the dimension is, there's a diffusion equation for the dimension, whereas not that the dimension is constant.
I agree. I mean, but in these cases, just as our starting point, right? These are graphs in which the dimension is roughly constant. It converges to a roughly constant thing as we change the number of time steps, right? Different from the behavior we're expecting to see. But these pictures are the kind of thing we would expect. But what we expect to happen is, instead of these things converging, doing what looks like a convergence to a fixed value here, we would expect to see over time that this estimator of dimension would change. Am I being confused here?
Yeah, I mean, you're not being confused. But yes, I mean, we're looking for dimension change. I think we agree. Right.
But these very naive pictures which are being done for rules that change the structure of, that change the overall size and so on. So the question is, if we do one of these for something that doesn't change the overall size, what will this do? And we can obviously just compute this, right?
Right.
So we take one of these pictures here.
You're then extracting a single number from one of these plots, which requires you implicitly defining a cutoff radius.
Oh yeah. I know. I mean, this is doing something. This is doing a violent, horrifying thing.
And in the cases where you're saying it's stabilizing, you are assuming that cutoff radius increases as the graph radius increases, right? You're going further along the x-axis as the number of time steps goes up in those plots, aren't you?
Indeed. Well,
you're already computing something different to what you said you wanted to compute 5 minutes ago. Because in what you wanted to compute 5 minutes ago, you were saying, I want to truncate the x-axis at 20 and do that.
I mean, does just make that a larger portion of the x-axis is going to be a valid place to place that cutoff?
Potentially, but I don't. Intuitively, that seems right, but I'm always worried about taking these limits where we don't know that they commute, because it's.
I know, but that's why we can do experiments and see what actually happens. But I mean, so what we're looking for here is we should just get a rule that doesn't change. I mean, what we should do is, what the heck is going on here? Why is it doing this? What the heck did it just do? It's crazy. Let's take an even smaller case here. This is, I'm running the latest version, I think, an overnight build. Oh gosh. What is this doing, and why is it showing that with the old-fashioned? Well, it's nice that it's starting all my computers, but it's a little bit obscure why it's. I don't know why it needs to do this. Always good to give them some exercise, though. Otherwise, they get, I think it's like horses or something. All right, that's our plot. Okay, for this case. Now, what we want to do is take one of your sprinkled, what we want to do is we want to take a rule here. I think you had a favorite rule, Jonathan, that you used in your relativity computation paper a favorite rule that doesn't change size. Is that correct?
Yes, although the important thing about that rule is that it doesn't change dimension. Like that's what you want for that. It also doesn't change size, but
How do you know it doesn't change dimension? Could you prove that? It seems very hard to prove that.
no, I didn't prove it. It just
Okay.
does. I mean, it seems to preserve dimension, and it also obeys the Einstein equations, which is equivalent to preserving dimension. And so,
Well, should we
heuristics-
try? I mean, okay, so you're claiming that even if I start the thing with very high dimension, it will. Can we try it? I mean, what is that rule? And then what I'm going to ask for is some kind of appropriate high dimensional sprinkled ball, basically. Is that what I want? A sprinkled ball in 10-dimensional space or something? How do I get a decent 10-dimensional or 5-dimensional, whatever it is, system? Jonathan, we lose you?
No. I don't. I mean, I have nothing to add to.
Well, but you have code that does this, right?
Yeah.
The first question is, what is it? Can you put your rule, either dictate your rule or put your rule in chat or something, so we can.
Let me dig it out now.
Okay. And then my question is, your sprinkling functions, don't they? Can we get a random approximation to 5-dimensional space from your sprinkling functions? I would think we can.
Of course, as we did last time.
Oh. Okay. I don't seem to be able to find what we. Let's see. Okay, so you claim this thing here is our first approximation to a 5-dimensional object. Let's just see what it does for 3 dimensions. I can't tell what this is. No idea.
Well, if you want to see it coordinatized, you can call spatial graph.
As opposed to pure spatial graph.
Right.
Okay, that's fairly lovely. All right, so that is the interior. That's a 3-ball. Is that correct?
No, this is a flat. You called flat manifold the graph. So this is a flat region of a Riemannian manifold.
Okay, how do I call?
It would be cubical.
What's that?
Yeah, it would be cubical in the limit.
Okay, fine. So how do I call a sphere? How do I make a sphere?
Probably the easiest way is to use extrinsic curved manifold graph, and then you just give it the equation of a sphere.
I think we have one of those examples here. Okay, and what I'm giving it then is
So we were getting the equation of a torus, but for this we want to give it the equation of a sphere.
Okay, so I'm basically saying x squared plus y squared plus z squared plus w squared or something.
Yes, yeah, if you wanted to.
Equals 1 or less than 1?
Well, do you want the surface or the interior?
I was hoping for the. What do I want? I think I want the surface, actually.
Yeah, I think you want the surface.
Oh God, discretized region only supports dimensions 1 through 3. That's lame.
Ah, okay, that is a problem. You could use intrinsic curved manifold to graph, but hang on, that may also cause issues. wasn't aware that discretized region had this limitation.
I didn't think it had that region, the limitation. I didn't know that at all. It's taking its time here. I'm a bit unconvinced. Oh my gosh, it's not even interruptible. Oh yes, it is. Okay. Okay, but so the objective here is to get some. Okay, were you going to send your famous rule?
Oh gosh, yes. There you go. Let's look.
Okay. Okay, so that's that rule. And so let's say that we, for example, were to do that starting from this object here. I don't know if that's a reasonable object to start from, but we could just try that. So if I say edge list that. What is this? Oh gosh, those are the labels of that, right? So I might want index graph of this.
Right. By default, all vertices are labeled with their coordinates.
Okay, all right. Okay, so there's that. Okay, so now I could, if I wanted to, compute this quantity here. All right, I have no idea what this is going to do, but this is going for 10 steps. Arg, what is it doing? Now, before we do that, let's just do something simpler. Let's say we, gosh, I don't use these things well enough. What is it called? States plot state. Is it called states plot list?
I think it's plots list, but it's been so long since I used Wolfram model.
Humph, what's it doing? It's not encouraging. Let's just do one step. What the heck is going on? That's very weird. Okay, if it doesn't even do 0 steps, I'll know there's something horribly wrong. Humph. Okay, well, we can try a smaller version of this. That's not a very convincing. Well, let's try the most obvious kind of, let's just try a random graph, because that's kind of what we want to have. Actually, random graph, you don't even need to do random graph. You can just say random, well, yeah, okay, let's do random graph. Okay, if we just did random integer, say 100, that's not enough. That needs to be like 200 comma that. Okay, we say graph of rule triple at this. Okay, great. Okay, so this is going to make us essentially an infinite dimensional object. And so now we want to run this with your rule. Not encouraging. Okay, there we go. So I think we've seen similar things before. This is effectively your rule cooling down that object there. Making sense?
Right.
Does this dimension estimator go bonkers when the thing is disconnected or not?
Which dimension estimator? My dimension estimators have an ability to set a graph radius, which will go to infinity if unchecked, but you can set it to be finite, so it doesn't care.
Does this work here, or is this going to go bonkers?
I have no idea. I didn't write that code.
I did, so I should know what it does.
Right.
And it's going to go bonkers.
Right. So if you use this dimension estimator, you can.
Which dimension estimator?
Well, for this, I assume you want to compute Wolfram Hausdorff dimension. So
why not? I think it's a terrible responsibility having a, one of these, because then it's got to better be the case that I actually understand what the estimator does, and that's very embarrassing. If okay, here we go. So this is for this thing here. Just 1 second. I need to remind myself of something here. Okay. So here we go. So this is what's this drop thing? Who knows what that is? Okay. Estimate list. I wonder what that's doing. Well, let's see what it does if I just do this. That's not encouraging.
Right. As I say, you need to, if you want it to not go bonkers, you need to specify a radius cutoff, because otherwise it will use the graph radius and that will be infinity.
Okay. Is that going to work? Okay, let's look at this more carefully. Okay, so first of all, oh, well, that's really stupid. I don't want to do that. Okay, I'm not dropping by that. I don't think I want to do any select. This is irrelevant. That's, go ahead.
I'm confused about what exactly you're calling. I mean, so I thought you wanted to get a list of dimension estimates, right? For different radii.
Do.
Right. So you should do Wolfram Hausdorff dimension, that of hash, all dimensions.
Okay, well, which hash, all, what?
All dimensions is the property that you want.
Okay.
I think. But then after all, you then want to specify your cutoff. So you'd want to say 10.
Okay, like that.
Right.
Okay, let's get this to begin with. This is the states list thing. Okay, fine. We've got a bunch of states lists there. Okay.
Oh, wait. Sorry. Yeah, the Wolfram Hausdorff dimension expects a graph, so you would need to say, undirected edge at.
Okay, let's take a look at what this is doing.
Could
So
be
this,
a modern art piece.
I'm sorry?
I'm saying that could be a modern art piece, but I don't think it's what we want.
Okay. What is this showing, Jonathan? This is showing for each one of the elements of the states list. What is this giving us?
Well, it's giving you the dimension at each vertex.
Okay, so what I want to do for that then is to say values of that, or is there a different accessor other than all dimensions, like average dimension? Or is there an around?
Well, there are options for all of these things, but be clear about what you actually want to do. So do you want to get the dimension at each vertex, or do you want to average out over all vertices?
I'd be happy to do this.
Okay, well,
I think I'd be happy to get this. Okay.
Well, you should know that there are options. There's vertex method, dimension method, volume method options, which tell you essentially whether you take minimum, maxima, or averages over all vertices, over all possible volumes, or all possible dimensions at each vertex.
Okay, those are all magnificent. But
Okay.
what this is now doing, okay? This is the extremely, unreliable version of what we're trying to compute. This is this dimension computed with fixed cutoff size 10, right? So let's look at this for 10 steps, for example. It's kind of weird. Okay, so let's look at this as we change this here to like 400. Humph. Okay. Okay, so this is the effective, with respect to this. So I wonder how that varies with the 10 there. Huh. I mean, if I try and that should hit the side of the edge of the graph most of the time. It's much smaller. Okay, so just for the hell of it, in here, what happens if we evolve a large number of steps? Oops, that's the wrong thing to look at. That's that one there. Okay, so I'm suspecting what happened there is that pieces of the universe fell off, and eventually we were down to something trivial there. Oh, this is okay. Let's say 20 here, and let's say graph undirected edge at hash. Map it over this. Let's just do 10. See what that looks like. What the heck? Oh, it's because I already did a states plots list. Okay, so that's what this is doing, right? It's untangling itself. And it's becoming very disconnected, which is something I didn't expect at all. So what's happening here is, in effect, this is doing sort of what we expected. Namely, it's going from a high dimensional initial state to something where it's a fragmented lower dimensional thing, right? Because I'm sure if I take that connected component and look at its effective dimension, it's going to be quite close to 1. Do you agree?
Well, yeah.
So in fact, this is doing what we intuitively expected to have happen. That is, except it did one thing that I didn't expect, which is this disconnection business, right? It's going from something which is highly connected, high dimensional, to something which is, well, I mean, I don't really understand this behavior here, why this is effectively going, I don't understand why that starts low and goes to higher dimension. I don't really understand that. But what it's doing is it's untangling itself to end up with this quite low dimensional thing. Okay, so you are now going to tell me that this is a totally undefined process that we're going through and that limits don't make sense here. But what I'm trying to understand is, what is the continuum approximation to what's happening here? Jonathan is silent. We've so upset him by exchanging limits that he's speechless. No, but
No, I mean, there's a lot of things there which I don't know. It's probably not worth talking about all of them.
Well, say okay. The thing we're trying to do is, what is a continuum limit approximation to the behavior, the kind of behavior we're seeing here? That's the original question we're trying to answer.
Well, it wasn't the original question. It's another question.
Why is that not the original question?
The original question was about manifolds, right? It was about, you start from an infinite dimensional manifold and it converges.
I just said an infinite dimensional thing. I wasn't, whatever. Yeah, I mean, you can only really define that, I suppose, for manifold. But okay, fine.
That's why this is becoming more disconnected than one would expect, right? Because it has there's no cohesiveness of the spatial structure, and this is a rule that preserves cohesiveness of spatial structure. So, I mean, yes, okay, fine. There's another question, which is, if we just start from some arbitrary thing and we define an extension of dimension for that thing, what is the continuum limit of that? But that was a different question.
Oh, fine. But I'd be happy to see. I mean, my intuition would be that there's going to be a generic answer.
Okay.
And that there will be all kinds of corner cases, but there will be a generic answer, just like, just like there's a generic diffusion equation and so on. That's my guess, is that there's a way to think about this so that there is a generic kind of decay of dimension result.
Right, but the diffusion equation is an excellent example of this, right? That the diffusion equation works really differently for an arbitrary metric measure space than it does on a manifold.
Explain. I mean, diffusion on like a group or something like that. What are you talking about?
Well, just, you take some metric measure space, or generally you take some space, some measure space that's equipped with a sigma algebra. You can define a Markov process, so you can define a diffusion equation.
Yep.
But the nice sort of intuitive properties of the diffusion equation assume that space has has some manifold like qualities. For a general metric measure space, it looks very different.
But actually, isn't that exactly? No. I mean, look, the whole point is the diffusion equation itself, in effect, it probes the space. The heat kernel effectively probes the space and gives you certain properties of the space. And so I don't understand what you're saying by the fact that, by saying it behaves very differently. I don't think it does it? What aspect of it behaves so differently? I mean, in other words, it is a little bit circular what's happening, because you're saying the heat kernel, the behavior of the heat kernel determines certain aggregate properties of the space, then diffusion behaves a certain way in that space because the properties of the space were, were determined by looking at what the heat kernel did in that space.
Yeah. I mean, the diffusion equation, maybe we're talking about different things. My understanding of the diffusion equation is it's just a relationship between a partial time derivative and a del operator. Right. That's kind of
well, that's its simple manifoldial form. But in general, it's what's that?
What's the more general form?
The more general form is just to say you've got, like on a graph, for example, you're just saying, you have some weight at each element at each node in the graph, and at each time step, you update it to be some average of the neighboring nodes.
That's not that's relaxation.
Well, in the limit, it's the same as diffusion.
Well, no, it's not. That's exactly I mean, yes, sure. There's a relaxation equation on graphs, which is on arbitrary spaces, which is just trivially defined like that. Yes, but there is a notion of differential operators for graphs, and from things like Kirchhoff matrices and so on,
which are, by the way, the same as this relaxation story. The Kirchhoff matrix is just the relaxation story. It's just you take the sum of the neighboring elements minus the one in the middle.
Yes, but again, the Kirchhoff matrix for weighted graphs is not uniquely defined, because it's unclear whether when you subtract the adjacency tensor from the from the adjacency tensor. Okay, when you subtract the degree tensor from the adjacency tensor, it's not clear whether both contain whether both should inherit the weighting or whether only one should inherit the weighting. And so the point is that when you try to derive a continuum diffusion equation, it depends on subtle details of how actually you define the differential operators, which is not the case in the manifold.
I know, because you don't have the notion of weighted. In a graph, you can go point by point, and you can say you've got weight 2, you've got weight 1, etc. In a manifold, you don't get to do that.
Yeah.
Right. I mean, in a manifold, you can only have continuously varying things, as opposed to just every point for itself, so to speak.
Yeah.
So my intuition would be that both the diffusion, yes, you can define exotic diffusion equations where you are going point to point in the graph and changing the characteristics and so on. And that if you do it pathologically enough, you can sort of you can reverse engineer what's going to happen, and you can cause all kinds of weird things to go on. But if you don't do that, my guess is that the thing you get at the end of it is essentially the same sort of large-scale diffusion behavior that you would get in any other case. And the intuition here would be that the same sort of thing is going to happen here. That, in other words, the question is, what is the characterization?
If that's a theorem, that's really, really interesting. I mean, that's because that's profoundly non-intuitive to me.
It seems okay. So it is somewhat intuitive to me, which maybe my intuition is wrong. But look.
No, I mean, you've thought much more about this than I have, so I'm prepared to go with your intuition. I'm just saying, if that is a result, and if that's been proved somewhere, then I'd be really interested.
Right, but it's my impression about how it works. I don't know what there are endless. Okay, let's. I know who I can ask. I will ask a question. I'll probably be told I don't know what I'm talking about, but that's okay. Okay, but let's come back to the dimension case, all right? Because the question is, if we're just looking at growth rates of geodesic ball volumes, the well-defined question that I'm trying to ask is there, I mean, and this is what we had talked about previously, about dimension tensors and dimension diffusion and all this kind of thing. I just don't have my brain properly wrapped around this question of whether whether it's obvious for some diffusional type reason what happens when you have a local rule operating on this hypergraph? What does it do to these growth rates of geodesic balls? Does it, in one situation, I mean, so what we want in the end is that there comes a point where it locks into a particular dimension and then says, I'm leaving that alone. Dimension 3, whatever it is, right? What causes it to start at a different dimension? And then what we would have to believe is that something about the rule, not the initial conditions, almost certainly, something about the rule causes it, local rule, remember, causes it to say, I'm going to asymptotically go to a fixed dimension. Which, I mean, in this case that we're seeing here, it rather bizarrely in this estimate goes to dimension 0.5, which I don't understand at all. But I mean, this picture does do something, although it no doubt does it for pathological reasons. This does do something which will be pretty encouraging for the universe. Right? That is, it starts, well, admittedly, it starts there with a different dimension, but what it's doing is it's getting higher dimension, it's decaying, and then it's going to a fixed, albeit kind of silly dimension here. I mean, that's the kind of picture that we would like to see for a mean field theory of a sort of continuum limit of dimension change in the early universe.
Isn't that last part just the evolution halting?
Oh, it could be.
Am I just missing?
It could be. Yeah, it could be. Could be that. Could be very trivial. Okay, so that's not interesting. All right, so it's pathological there. But the question would be, and maybe if it didn't halt, the thing would just keep going down to smaller and smaller dimension. I don't know. Right, but that's what we have to explain is what is the initial, is there a good continuum approximation to that initial decay of dimension? And I'm just still trying to wrap my brain around, okay, so when you derive the diffusion equation, you say, I'm going to look at the local density of particles in a particular region, and I'm going to write down a differential equation that describes, the net change of particle number as a function of position. Is there an analogous thing to do in dimension, for dimension? And maybe there's a way to think about that in terms of these geodesics and in terms of the number of geodesics that I don't know. I mean, I don't know how to think about that. I mean, maybe this is a story similar to what we were talking about last time of where the rule is operating. Okay, so here's a question. So the rule is operating at the level of individual nodes and individual edges. But what is the effective operation of the rule on geodesics? So the analog in fluid dynamics would be you're looking at the operation of things on the velocity field, but then you ask the question, what does that do to vorticity? Jonathan, do you have thoughts about
well, you're obviously you're exchanging segments on nearby geodesic paths. That's what a general rule does.
Okay, that's a nice way to think about it. All right, that's the kind of thing I was looking for. Okay, so if that's our mean field theory concept, what will it do? Okay, look, you've got some space. It's got geodesics that have some fanning out rate, which is determining which is determining the effective dimension. Now you randomly, the analog of diffusion is you would randomly be exchanging nearby geodesics, which seems like it's diffusion in geodesic space of some kind. What would that mean?
Is that a rhetorical question?
No, I was hoping you would answer it.
Well, my view is simply that it's the same, homotopy versus vibration story that we were discussing the other day in the multi-way system context, right? What really matters is the horizontal translational distance versus the vertical translational distance.
Okay, that's a very interesting claim.
Right, because what you're really saying is we've got geodesics that they are, as you say, fanning out. The rate at which they're fanning out determines the dimension. So I've got a rule that's exchanging geodesic segments for other nearby geodesic segments. So they're going to be, some are going to be transported sort of, along the direction of the geodesic. Some are going to be transported laterally to the direction of the geodesic. And then the question is, does the rule transport more laterally or more longitudinally, if you see what I mean?
Yeah, I get what you mean.
Right. That will determine effectively whether the dimension is changed and in what way.
All right, so let's write down this intuition. Okay, so the claim is, in a given dimension, the dimension determines effectively the fan out of geodesics. Then the claim is that we'll call it, segment exchange. Can be between fanning out geodesics, but between it can be either in the fan-like direction or in the orthogonal direction, or in the cross-fan direction, cross-fiber direction. Right?
Right. And in general, cross-fiber motion will not change the dimension, but fan-like motion will. And then it matters whether it's, whether it's a net motion, forward or backwards along the fans, along the fan blades, so to speak.
Let me understand that claim. So basically, the claim is in cross-fiber is like moving material around in a given shell, in a given spherical shell, while fan-like is concentrating radially or not. Is that right?
Right, something like that. Yeah, I mean, so certainly cross-fiber is moving material around in a given shell. I don't quite know what you mean by concentrating radially, but what what it's doing.
So what I mean is it's like a star collapsing or something. I don't know what. It's a change in the amount of matter as a function of radius, isn't it? That's what it means to be. Okay, how exactly does that work in a segment exchange in a fan-like direction? That's effectively changing.
Well, you're changing the number of edges appearing on a on a shell, not on a given shell, but between shells. Right?
In other words, what you're doing effectively is deforming the sphere to pull the thing into a shorter distance to get to a given shell or not.
Right.
Right. So you're deforming constantly radially or deforming the radius of shells. Okay. So now I bet there's an issue here, which is what is determined by essentially your topological dimension, which is if you are randomly doing segment exchange, the probability that you are in a fan-like direction is determined effectively by topological dimension.
Yeah, I agree.
Okay, so the probability for a fan-like change is determined by effective topological dimension. And so what is that relationship? So how many, is there only one radial direction? Yes, there's only one radial direction in this setup. So effectively the probability of a fan-like change is 1 over the effective topological dimension. Am I right? And now, what's the other part of this? This is about to become a diffusion equation of some kind. What's the other part of this? So the volume element is determined by the Hausdorff dimension, not the topological dimension, right?
Yep. Again, accounting for the fact that you're implicitly taking a trace in this derivation.
Well, because I'm using geodesic balls, I'm not using something more like your finer Riemann tensors.
Right, right. So anytime where you get this mixing of topological and Hausdorff dimension, it's a sign that you're taking a trace somewhere.
Right. Okay, so the volume element is defined by the Hausdorff dimension. If we made the outrageous assumption that these dimensions are the same, which might not be correct, but let's assume they're the same, then can we write down the equation for what's going to happen here? This is the probability for a fan-like change. So every element can either move in the fan-like direction. So if it moves in the fan-like direction, it is taking the dimension, let's call the dimension D, for example, it's taking the dimension, the probability that it moves, right? So what we've got is an equation that says, partial with respect to time of the dimension d of t. That's the probability for a change per unit volume, I think, is something like how does this work? No, it's like a kinetic theory argument. You got to be able to go. It goes both ways. It has a probability of changing. Yeah, it's a little bit trickier than this. Oh boy, I'm going to have to break out a piece of paper here. This is really shocking. Let's see if I can use my fancy. Let's see. This is terrible. This is actual paper. Let me see whether technology can help me here. Okay. Let's see. Let's see what happens here. Let's see if I can make this work. Oh, come on. What do you mean timed out? How could it be timing out? Host is down? How could the host be down? The host is sitting in my hand. No, it's opening Xcode. Help! By the time it's opening Xcode, we're not in good shape. Did this? This is very frustrating. I was trying to use my tablet thing. Oh, drat, why isn't this working? Should be working. Let's see. Fancy that. Well, so much for the okay, let's see what happens here. This could be really scary. I'm not used to doing this at all. This is kind of from the old world, more or less the old world. Okay, help me, please. All right, so what we're trying to do is we've got this concept that we've got sort of an element here of okay, we've got this whole sort of fan-like thing, right? And our concept is that we have an element here that is going to either have an interchange with, you know, a azimuthal interchange or a radial interchange. Is that right? Jonathan, help.
Right, and so the change in dimension is given by the infinitesimal ratio dr by d theta, if you parameterize these by r and theta.
Explain. So you're saying to explain that for a second. So what are you suggesting I write down here?
Well, so for computing the dimension, you would take this collection of outgoing geodesics and you would split them up into shells, right? And then you're asking what's
Okay. So I've got some shells here. Yep.
Right, and so effectively what that's doing is that's effectively dividing up a space into boxes in a polar coordinate system, right?
Indeed, yes.
You've got an r coordinate and a theta coordinate.
Yeah.
And then so what matters is dr by d theta, right? If you're assuming that the rule is effectively just uniformly sampling all possible collections of nearby edges, which is probably not a very good assumption, but let's stick with it.
Mhm.
And yeah, so what matters is dr by d theta. And that's actually it's a little bit more subtle than that, because in reality it matters. It's not just dr by d theta. It actually matters specifically what r is, because if you shift things around, if you shift things down, if you shift elements
down one of these fibers, yeah,
with an increasing r close to the origin point, then that will tend to, that will tend to decrease the dimension, whereas if you shift it further along, it will tend to increase. As indeed we saw previously, right? That you, in those situations where you got sort of temporarily increasing dimension, then a sudden fall, because effectively you were deleting edges on the interiors of shells, and then eventually a whole section would become disconnected, and that would cause the dimension fall. So it matters how far along radially you are when you shift this stuff around. So you have a dr by d theta dependence and an explicit r dependence.
Okay, I partly understand that, but let's see, can we derive, okay, so you claim that by just sort of randomly shifting things around in this sort of radial setup, what I want to derive is what the equation,
Right. Yeah. I mean, I think I have a procedure for effectively deriving.
Okay. What do we do next? I don't know how to do this, and this is very scary because I'm writing math by hand, and that's not something I usually do. And actually, I need to attend to something for just 1 minute. You can ponder this for just a minute. I will be right back. I'm sorry. And then you'll either have figured it all out, or we could have dueling tablets. Do you have such a thing?
I don't have a tablet. No, I'm too old-fashioned for that.
Okay, we'll have to get you one of these. This is a very cool object. I originally gave these gifts to my kids, and they decided they were wonderful, and then convinced me that I should use it too. I'll be right back. Just a second.
Sure. How are you doing, Jean?
Oh, well, still just university stuff mostly.
Okay. Has term started for you yet? I know you were off for a while, but
Yes. So my first term ends at the end of the month.
Okay. Wow, that was a short term.
Yes. It's I think 7 weeks, I think.
Oh wow. Okay. I thought the terms at Cambridge were short, but seven weeks is pretty.
Yeah. Yes. Our semesters are usually 13 terms of class, and then long time that's just exams basically.
Right. Are you a tablet? Sorry.
Yeah. Sorry.
No, I was going to ask a completely unrelated.
I'm not sure if my internet or your internet died there.
I think that was Jonathan's. It got all scrambled for me as well.
Okay, that was scary.
Oh, I'm sorry. Okay, can you hear me?
Yes.
Hi, sorry. I think I disconnected my audio setup. No, I was about to ask you completely unrelatedly whether you were a tablet person or not.
Oh, no, I do not have a writing tablet, although that might clear up a lot of the clutter I have. I still have like, I think, yeah, more than 100 handwritten pages that I still have to file that are just in the same fault binder thing that I hold my notepad in. So it's just very cluttered. So that might help that, actually.
I think there's something kind of charming about having an office that's filled with like unfiled papers. That I'm worried one would lose something by switching to purely tablet.
But the remarkable over here, it converts all your text into, all your handwriting to text and whatnot, and you can save the original document. So definitely worthwhile.
Yeah, people have been recommending the Remarkable for a while. I feel like I should get one.
The remarkable too is, I kind of wish that we could partner with them to, yeah.
How much do they cost, though?
The remarkable 2 is around $300 some. The remarkable 1 is more, but
Okay.
remarkable 2 is way better.
South African currency, that's quite ridiculous.
And American currency is as well.
Right. Yeah, living costs in South Africa are so low.
Yes. So importing anything is usually quite an issue because the costs get high relatively to what we're used to.
Sorry, we were talking about tablets. This is
the thing that's nice about this one is it's like a piece of paper, so I'm seeing everything that I'm writing, right?
Is that the remarkable 1 or the 2?
It's 2.
The 2 is excellent.
Okay. In any case, Jonathan, you were tell me how to do this derivation.
What element of it? I mean, this is a complicated thing to do. I mean, like I say, I think I have a picture of how to do it, but
okay. Well, I mean, but give me a rough.
The current setup that we have is this is a procedure for deriving an elliptic equation, not a parabolic one.
I don't care that it isn't a diffusion equation. The fact that it might turn out to be a diffusion equation or not is not. I mean,
because if you want to derive a parabolic equation, this is assuming effectively that there's an infinite supply of geodesic segments. Whereas if you wanted to derive a parabolic equation, you'd have to assume that wasn't the case. And that's more complicated. I don't know how you deal with that.
See, the thing that I'm thinking about is it's like a kinetic theory argument, right? Except that this is I don't know how you do the analog of kinetic theory for vorticity in a fluid, because this is somewhat like that. Again, it's not quite the same thing. But this is, in other words, look, how does diffusion work? How's the diffusion equation thing work? Well, you've got some lattice, let's say, and you've got a bunch of particles on the lattice, and you've got some particle here, some particle here. The particle has a certain probability to go there, a certain probability to go here, etc. And what you're doing is you're saying n of, some n of x. Let's just do the one-dimensional case. Okay, let me remind myself how this actually works. The probability, right? So you have a certain jumping probability, p, let's say, and it's p n of x plus 1. So if we're trying to work out the new value of n of x, it is n of x plus, let's see, minus the probability that you jump away from x. Yeah, right. So it's just this. It's just something like, if the jumping probability, right. This is trivial. Okay, minus 2p n of x plus p times n of x plus 1 plus p times of n of x minus 1, right? And then that's that whole thing is equal to n of n prime of x. So then, oh boy, I'm not yet used to or skilled at the use of tablets because I've used up my space incorrectly. So if I say delta t of n of x is equal to this n of x minus plus p times, that's delta x n of x minus n of x, I think. Actually, that's otherwise known as, sorry, this here is more correctly known as the second derivative, right? It's an approximation of the second derivative, whatever it is. And there's probably a minus sign there. Yes, there is. And so that's our diffusion equation, roughly. I mean, this is standard kinetic theory stuff. So then the question is, what is the analogous thing here? Where the measure of what, in this case, that's all trivial, but you want to figure out, yeah, okay. I mean, there is presumably a derivation along these lines. Yeah, we should probably wrap up soon here. I think we have made progress on this. At least I feel we've made some progress. Jonathan, do you think we made progress, or have we only been going backwards and being the?
No, I don't think we've gone backwards. I mean, but this argument, essentially this.
What's that?
It requires, like I said when I first proposed it, I think it requires work to do, which I haven't had the time to do yet. Hello, sorry.
Yeah. No, I'm just thinking. I mean, roughly what form? So this thing roughly is here. We can now take this, because we live in more modern times. We can take that and we can paste it in here. I could also upload it, but I could also just paste it there. Not that it's very useful, but yeah, so what do we think is going to happen here? So we think this is going to give us a dynamical equation for dimension. Curvature is not showing up here. Why? And should it? Or can we talk about dimension without having to talk about curvature here? And also, I think this is not going to have the problem with finite size universe stuff. I think this argument is going to be completely, infinite universe friendly. Because I think it's basically just a kinetic theory argument where the measure is weird and where there's some sort of yeah, so I think the end result is going to be some continuum equation for the dimension. Do you agree? I mean, independent of curvature.
Well, yeah. Again, when I proposed it, that was the idea.
I have lost exactly what you proposed here, but that's okay. Doesn't matter.
No. What do you mean? The geodesic segment exchanging was exactly the same idea that last year, right? And so this.
Wait. You proposed when?
Equation
Have I completely misunderstood this for all discussions of this? Well, it's a good idea anyway.
Well, yeah, it's the direct analog of how you derive the continuum equations for extrinsic curvature on space-like hypersurfaces as a time evolution problem. But just like there, you have all kinds of horrible issues with gauge dependencies and things. As I said at the time, I think you'll have at least as bad problems for the dimension case, because dimension is even more sensitive to gauge choices and stuff like that. But anyway,
what's the analogous derivation that you're talking about?
The continuum equation for curvature.
Okay.
Which is the evolution of the extrinsic curvature tensor on space-like hypersurfaces, which depends sensitively on where what your gauge driver.
Yeah, I mean, I guess I had not understood the concept of that being a kinetic equation for exchange of geodesic segments.
I'm sorry.
That's obvious. What's that?
I missed that. What did you say?
No, I said I had not understood that could be thought of as a kinetic equation for the exchange of geodesic segments. is that obvious? I mean, it seems plausible, but
It's not obvious, so that's why it requires a proof, right? But that's,
okay, that's an interesting concept. I mean, so okay, so then,
but I mean that's the whole basis of the discretization of the Cauchy problem that is presented in some of the more recent stuff I've been doing, is that you treat the evolution equation for the extrinsic curvature tensor that you get from discretization of the Cauchy problem as a purely kinetically derived thing from exchange of geodesic segments, because
well, it's a nice interpretation. Okay, I hadn't got that from, maybe it's written obviously on some page. You see,
But you see my argument, right? That with that, there's already a huge stack of problems with gauge dependencies. And my suspicion is, although I haven't proved it formally, is that those problems will be at least as profound for the dimension case, probably more so.
Okay, I naively think the dimension case may be more robust, but we'll see. I think dimension is a coarser measure, and it will be less sensitive to those details, but we'll see.
Maybe.
But the end result here should be, okay, the end result should be an evolution equation. We should be able to derive get the direct analog of the homogeneous isotropic dynamic dimension universe. So that'll be interesting. I mean, it's got to, I think it's clear from all of this, that's going to exist. There's going to be a continuum description of this.
Right, I agree. But an alternative way to derive that, as we mentioned, may be to understand exactly what conformal, what the analog of conformal rescaling would mean for dimension change. But we seem to have moved away from that.
Well, do you think you have a way to think about that? I mean,
no. I mean, that's why I thought it was an interesting. It's one of the few things I hadn't thought about so far.
Okay, so hold on. Let me see. Now that I've got my tablet out and things, and I've got I have the technology for it. Let's try drawing. Remind me what it looks like. What is the sort of conformal structure of I'm sure I can look this up. The conformal structure of the FRW. What does it look like?
I'm sorry, my microphone is cutting. My speakers are cutting out. The conformal structure of what? Sorry.
Of FRW.
Oh, I mean, that's just uniformly. That's just light cones that are either uniformly moving away or moving towards each other, or staying.
So wait a minute. So we've got something where, starting from the beginning of the universe here, we've got a bunch of little light cones here. And what does it look like? Does it look? Is that? Are you saying it looks like this, where there's a sort of a big light cone and then there are lots of little light cones inside it, which means that conformally this thing is just going to be, no, I don't quite understand. It's going to have, what is the right structure for this?
Well, as I say, effectively the divergence of light cones is either is monotonically, is either positive zero or negative everywhere.
Okay, what does that mean that it looks like? So we're talking about a conformal diagram which shows the paths of, essentially the space-time paths of photons.
Yep.
So what is the correct picture? What's the picture for, in the case of curvature 0, k equals 0, don't you effectively get a big light cone with lots of little light cones inside it?
Sure.
What do you get for k not equal to 0?
I mean, you get the same thing. It's just that there'll be a divergence that's not 0.
But if I draw the diagram, so if I draw the causal graph, I don't know how to convert this to causal graphs and things. The continuous, Penrose diagram-y type thing. Okay. What I mean in sort of a causal graph type setup, the obvious kind of Minkowski space causal graph would look something like this, right? So what does it look like in the FRW case?
I don't understand. I mean, the causal graph doesn't look like that for Minkowski space, so I don't understand, or at least we must have different definitions of causal graph.
What do you mean? That's a
causal graph with a Manhattan metric.
Fine. Okay. It's a lousy approximation to whatever the more realistic, thing with more effective randomness is.
Right.
But so what's the analogous picture for FRW?
Well, I mean, it's just depending on the curvature parameter, either the edges of the Horismos cone bow in, bow out, or remain flat. I.e. either the divergence is positive, negative, or zero.
I understand. I'm just asking, how do we look? Okay, the question is this idea of conformal invariance that's true. What does it mean? Okay, let's take it from the most basic thing. What does it mean to say that it is conformally invariant? It means, go ahead.
Sorry, to say that what is conformally invariant? What is it?
The FRW, evolution of the universe.
Well, if you take G mu nu and you apply a conformal factor omega hat, that G hat mu nu is, the signs of GXX for tangent vectors XX are preserved.
Okay, but more physically, if we think about it in terms of light cones and so on, what does it mean there?
Well, the light cone partial order relationship is preserved. Right, the interiors, exteriors, and surfaces of the light cones are preserved. Those are the signs of GXX.
Preserved through time?
No, preserved in the transformation.
What transformation?
The space-time, you just said a conformal. What does it mean to be conformally invariant? I apply a conformal transformation. This is a space-time metric, so they can't be preserved through time. That doesn't mean anything.
Okay, all right. Okay, space-time metric, and it is, we do this conformal transformation, we change its scale, and we say, does the causal structure remain the same?
Yep.
Okay, so what's the analog of that? What's the analog of the metric for what's the most relevant quantity for when dimension can change? Is it still the metric or is it something different? The metric gives a volume element. The square root of the metric gives a volume element, which is a relevant thing in all of these cases. But so what would we mean by a conformal transformation in the case of, in this dimension varying case? What would that mean? I mean, conformal transformation usually means you scale the metric, right? And I think conformal transformation in the more general case is the geodesic balls are basically the notion of radius is changed in these geodesic balls. Is that right? No, that's not right. That's not right. What is the analog of a conformal transformation in this more general setting?
What more general setting?
The one where we allow dimension change.
Why would it be any different?
Because I'm not sure the metric is the thing that we're most readily defining.
What are we defining?
All we have is this hypergraph that's evolving. And from that, we can, erect this whole set of things that leads us to things like Riemann tensors and presumably eventually to metrics.
Yeah, I know.
But I'm not sure that that's the most relevant thing to be looking at, is the transformation of the metric.
I agree. That's why we don't do that.
Right, so the question is, if we're trying to find the analog of conformal invariance in the case of the, dynamic dimension case.
That has nothing to do with the metric. The whole point of the causal graph is that you don't have to have a notion of a metric, right?
Yes. Okay, but so what's the analog? What's the physical analog? We just talked about the physical analog of conformal invariance in terms of the causal graph. So what is the analog of conformal invariance in the case? I mean, okay. Here's a question. What do we think the causal graph will look like in a dimension-changing space? In a rough approximation, we know what the causal graph. I mean, yeah, you don't like my Manhattan metric thing, but we roughly know what the causal graph looks like for. I mean,
it's not that I don't like it. It's just I don't understand what you mean when you say it's like Minkowski space.
Okay, fine, fair enough. Okay, I'll draw. I'm not a
I
very good. I can't draw a very good artist's impression. There. I'm going to. This is my artist's impression of the causal graph for Minkowski space, which is less useful, but perhaps there's a better way to draw this. I got a few arrows that sort of vaguely go down. Okay, in any case, what do we think that the causal graph would look like in the case of dimension change? I think we've thought about this. I've thought about this before. Anyway, we've probably been going too long here. We probably should wrap it up. All right. Progress has been made, I think. And gosh, I wasn't even looking. Let's see, are there questions here that we can address? Not really. Okay. Well, thanks both very much. And let's wrap it up here. So thanks a lot. Bye to people who might be on the live stream.